switched on. So mic 1 is where all the audio is coming in from the mixer. So we need to make mic 1 on, so now that we have that. We're live on, I'm just tapping.
Okay.
You see it coming through, coming up in here. I have this monitor on, I'm going to put monitor on. And then so we close this.
when you, Castile, this is all the PowerPoints for the speakers here.
Yeah.
So if you just double click on Castile,
I'll get ready.
okay.
All right, welcome to Phoenix, Arizona, AMSAT Symposium, Space Symposium. This is what, number 43? Number 43. So you can do the math. We've been around since 1969. They haven't always been going on. But anyway, welcome all of you. My name's Robert Bankston, the former president of AMSAT. Thanks to the generosity of a person I'll introduce here shortly. Oh, there it is. So let me get rid of some admin stuff here. Y'all came in the door here. Bathrooms right outside the door there. We have a water station. There's a few brownies left back there on the plate, if you're interested in those. And other than that, I'll be introducing the speakers. We have built-in breaks, and we'll break at 5. Any questions so far? No. So at this time, it's my pleasure to introduce the now president of AMSAT, Andrew Glassbrenner, K04MA.
Welcome, guys. Appreciate you guys coming out to Phoenix for the symposium. We got a lot of good presentations lined up for you. A lot of news out of our engineering team and our ascent teams, and hope you find them interesting. I'll be around all weekend. If you guys have any burning questions or issues or just want to introduce yourself, feel free to pin me down somewhere and shake my hand. I'd be happy to do that. And hopefully I'll be presenting during the general meeting, members meeting tomorrow, and a lot of new ideas and things we can do for AMSAT moving forward. So I'll keep it short and sweet so we can get to the good stuff. Thank you all, and have fun.
All right, first up is Cameron Castillo, KJ7ILB. I think you're just about the only guy here without gray hair, right? So, great stuff here. Let me get your slide going there.
We're working hard to make it clear.
There you go. Okay. Oh, the mouse. Okay. And then,
I think if you go up to like the 3 dots.
Did it just last year. Let's see. Actually, what we should do is
Maybe you have to open it as a Chrome or whatever. If you open Chrome and then
good point.
present it that way.
Yep.
And then the three dots is right.
Oh, yeah. There we go. There we go.
all right.
Hello. I'm Cameron. I'm one of the members of the AMSAT engineering team. I work on some other projects currently as well as the Propulsion, but I'm part of one of 3 members of the Propulsion team, and we're working on ways to basically integrate Propulsion into our newest. Oh,
Left and right.
does that actually work? Ah, perfect. We're working on ways to integrate Propulsion into our newest line of satellites. So, not necessarily Golf 1, but Golf 1 and beyond of what's kind of coming in the future. And so this is kind of on some of the basics of propulsion, and then some of the work that we've been doing over the past about year and a half. So let me start off. So I have a picture here of Fox 1A or AO85, and then compared with some of the other missions that we've seen sort of higher budget that people can do. And Propulsion and CubeSats have really come a long way since we've started launching CubeSats. I mean, we've had CubeSats for a long time, or AMSAT has. But you see, there's been missions that have been to Mars, been to the moon, that are doing, really complicated like GPS stuff. That's that Cygnus mission there. And I feel like there's a lot more enthusiasm about CubeSats and their technology, but a lot of this is sort of enabled by propulsion. And to get to those more, I guess, enthusiastic goals of what we could do, it's kind of required that we are going to have propulsion because we need to both increase our orbits, avoid collisions, and then deorbit is another really important thing that has become more important over the lifetime of our CubeSats. Unfortunately, miniaturized thrusters have really lagged behind other areas of development in CubeSats. I think it's a lot harder to miniaturize a thruster than it is, say, your radio payloads and different things like that. That's an important goal for AMSAT to be able to do propulsion on CubeSats, but obviously it's a challenge. But AMSAT has actually done things with propulsion before, and this is not our first round. If you all remember AO40, which I'm sure there are people who could tell me all about AO40 that maybe worked on it here. So I don't claim to be an expert on this or know everything that happened here, but it had a 400 Newton chemical thruster that it was supposed to be firing, and unfortunately it exploded the first time they tried to fire it, and it destroyed a bunch of subsystems on the Phase 3D here. And so I think that after that sort of development, AMSAT has not done any propulsion. And correct me if I'm wrong on that. I have not been on the team that long, so I couldn't tell you if there was more of an attempt after AO40. But we still want to attempt these things and sort of keep moving forward with our CubeSats, as I've said. So what does our propulsion development look like after this? And as it turns out, there's been a lot of development in CubeSat propulsion, and maybe these are some examples of what people have done before. So this satellite here is NanoSail D, which put out a Mylar solar sail and was actually able to show that you could do orbital transfers. It was very minor, but and then also deorbit using a sail. That was a 6U CubeSat, so a lot bigger than what Golf T is, but pretty ambitious mission, and they were very successful with what they ended up doing. This mission here was one of the, it was a propulsion unit that was on one of the Artemis II missions, and it ended up blowing up as well as AO40. And I put this on here before they had actually fired it, but that's an interesting story on that one. The thruster on the right there, on the top right, is an electrospray unit from MIT. It's sort of an experimental build, but one of the other propulsion team members and I, Jeff Vollen, went to the small satellite conference this year, and we saw actually people using really similar units to this. And as well, we also saw this unit on the bottom right, which is Morpheus Space. It's a FEEP unit. Where they integrate all of these individual feed thrusters. It's really hard to see in that pictures, but they're little circular thrust, I guess, modules that are you can sort of individually control, and so that gives you a sort of vectorized control over where that thrust is pointed. And so before we get started on propulsion, I thought it was kind of important to kind of define some of the parameters that we're talking about, because not everyone might be familiar with some of these, and they're not necessarily intuitive. Delta V is what you use to determine how much your orbit is going to change based on how much thrust that you're putting in from the propulsion system. And it seems kind of obvious there, like, well, obviously it's the change in velocity, right? But it tells you, if knowing this, knowing how much change in velocity you have, tells you a lot about how your momentum changed, and that can then go to tell you about how your orbit shape has changed as well. And so that's why it's an important parameter. Specific impulse is, again, it's sort of like the mass efficiency of the system. So the total impulse that you got versus the weight of propellant that you used to get that impulse. And it's also proportional to the exhaust velocity. So if we're trying to increase specific impulse, need to increase exhaust velocity while decreasing the weight of propellant that you're using. So that's sort of the trade-off there. And then, of course, thrust, which is, again, it's Newton's second law, but instead you take the derivative on mass instead of velocity. So same thing. But it might not be intuitive as to what these things actually mean. So they're generally, propulsion systems are like grouped into two groups. There's non-electric propulsion systems and electric propulsion systems. So non-electric, and these are like your liquid thrusters, like that was on, or bipropellant, sorry, that was on AO40. They generally have low specific impulse. They're not very mass efficient, so you usually have to have a lot of massive propellant. But they have a higher thrust, so you have to fire the thing for a lower amount of time. And they generally have lower power consumption, which is something that we're very concerned with in a Cubesat. But they are also larger too. And the electric propulsion systems are also, they get smaller, but you get higher specific impulse because they're generally using some kind of electrostatic method to expel some particle, right, of either liquid or gaseous propellant, ionizing things and then expelling them. And they're usually, you can get them a lot smaller, but they also take a lot more power. And they add a lot of complexity, but we'll talk about that. So going through, the first propulsion system I'm going to talk about is solid propellants. When we had started talking about propulsion systems, I think I had kind of considered these off the table just because they seem dangerous and not controllable for something like a Cubesat. You know, you see this picture here. This is actually a study somebody did. This came from an academic paper, so it's not just somebody in the desert with a. But they basically put an Estes rocket motor on the back of a Cubesat, and they're showing off this thrust vectoring system here. So that's what the point of this is they turn these little paddles, and that's how they're able to adjust the satellite. I don't know how much of a test they actually got from this, but. It illustrates the point of why electric propellants, or sorry, we'll talk about that later. Solid propellants are not generally feasible. They usually have really low specific impulse, but a really high maximum thrust. I think this thrust had 76 newtons, or this, and of course this is all for Cubesats, not for necessarily a larger engines. There are definitely engines that can do more than that. And I'll talk more about the work that we've done on solid propellants later, but that was kind of the state of what solid propellants are. Then there's liquid propulsion. They have both bipropellant and monopropellant, and that's where you have to flow some liquid over either a catalyst or react it with another liquid to create some kind of heated gas that you expel out of a nozzle. And that generally has a higher specific impulse. A lower maximum thrust that I could find for like units that were available for Cubesats. But I would say have a much higher complexity because you need a whole valve system. And it's harder to find propellants in liquid form that are not dangerous because what people used to use is hydrazine. And I think actually AO40 used hydrazine. And so that's not very safe to be working with and not something that we as a sort of amateur organization probably would be doing. Yeah. Cold gas systems, and I didn't put it in here, but warm gas systems as well, or steam, as we'll again see later. They usually have a pressurized tank or something, or some kind of compressed air or a refrigerant that turns into a gas as you expel it. You get a really low specific impulse and a really low maximum thrust, but they're not very complex, and you can 3D print these parts. Like that unit there is a fully 3D printed cold gas system, and it only has a couple of valves, and it was used to do why can't I think of the word? Attitude adjustment for a satellite that was needing really precision pointing. Which is not something we necessarily care about as much. You can increase the specific impulse if you heat that gas before it exits the tank. And one thing you might think of doing is putting water into one of these tanks that's completely non-pressurized, so you don't have to worry about having a pressure vessel for it to meet those sort of launch requirements. And then as it's turned into steam, vaporized, as it exits, you increase the specific impulse greatly and the thrust. So just something to consider there. Solar sails, these are, I don't think this is something AMSAT would be attempting, but they are something that has been done on CubeSats, and I just wanted to point that out. You obviously get a very low maximum thrust, so not something you'd be using for like collision avoidance, that kind of thing, but for orbital transfers over the course of years and years and years, this is a possibility. But anyways, I just thought I'd bring it up because it is something that, I think it's interesting that CubeSats have actually used this. Hall effect thrusters, this is the first of the sort of electric propulsion. They use circulating electrons in a cavity to ionize a gaseous propellant, and then use a static electric field to expel that, those ionized particles. These are usually really, really power hungry, and there actually are some commercial units, Hall effect commercial units for CubeSats, but we haven't really considered them because they're really, really expensive. And then they also, they're very performant, but at the cost of a large system. I think the smallest one I could find was a 2U system because you need to also have tanks for the gas that this thing is holding as well. So, and of course, they're very complex because they include both, a whole valve system and gas storage, as well as all of this complicated electronics. And then finally, if you could probably guess, you're kind of creating like a cyclotron, so you're ending up with the sort of noise that is caused by that when you have circulating electrons in the back of your, electrospray is another option in the electric propellants, and these generally use like a sharp needle to ionize a propellant or some kind of liquid propellant. Generally, this is like a porous substrate, so you have your liquid fuel down here, and it sort of like by capillary action works its way up through your set of needles there, and then the needles, because they're at a sharp point, ionize the fluid, and then that is what ends up expelling the particles at a high speed. So you obviously get very, very low max thrust, 2 millinewtons, but really high specific impulse because it's a very efficient process. And there's no moving parts in this, which is the great thing about this. So I think that this is one of the things that for a lot of larger CubeSat missions is really being considered. And this also, the FEEP also falls into the same sort of category here. But usually when people are talking about FEEP thrusters, it's larger needles, not like this. That would be very small. So pulse plasma thrusters, we actually have a pulse plasma unit back in the back on the back table there in that yellow box if anyone wants to check it out after this. But they use a sort of spark gap to ionize some propellant. And then that is what ends up being expelled, and you end up getting thrust from that. You get a really low maximum thrust, but a high specific impulse, lower than Hall effect. But these are generally more feasible for a lot of the things that we end up doing on a CubeSat. That's why there's a lot more pulse plasma units. This is one that was on, I think, or that was built by the same team as the HuskySat people, or the University of Washington, I think. And then there's also a group that kind of spun off from that does fiber pulse plasma units, where they feed a Teflon fiber through a sort of spark gap, and then that's what causes your, that's how you end up, it's sort of a different configuration than this. But that's another one to consider. So here's sort of a final list of, and again, this is just from doing a sort of research on what is available right now for CubeSats, or at least a year ago for CubeSats, and what's sort of the cutting edge, what people are writing about. And this is sort of the general conclusion that you can find from a lot of that work. So what has the Ascent team been doing? And I guess Ascent is the engineering side's, the AMSAT engineering team's like research and development section. Yeah. So we're working on sort of researching some of the feasible methods of propulsion, determining like what what we could actually do with propulsion if we got it via simulation, so both doing orbital simulations. We're also doing a lot of hardware testing and validating what technologies are feasible to put on a CubeSat. And then, of course, working with some industry partners. We actually have one of our industry partners here today, Troy, if you'd like to speak with him about some of the work that we've done with him. So some of the first things we ended up doing were trajectory simulations. So this was a trajectory simulation that I ended up doing. It's not very realistic. I think I strapped like a 3U thrust unit to Fox 1A or a satellite like a 1U Fox. So that's why it's you get this very large orbital change with what seems like with a 1U CubeSat. So it's not very realistic, but it just shows that we could do this type of transfer and simulate it. This was unfortunately all written with Python, and it's very slow. And so we have been trying to switch over to D2S2, which is what the rest of the golf team is using to simulate the satellite, right? So, and sort of taking their models and then integrating them with the propulsion units that we have available to us and sort of getting that data all together. But D2S2 is a little difficult to work with, so we're still working out the kinks there. So we've also worked with electrically controlled solid propellants. So like I said, I had kind of written off e-propellants, or solid propellants, but one of the members of our team is a real expert on this stuff. E-propellant, which is, it's solid propellant that you run an electric current through, and that's what causes it to fire. And so it's totally inert most of the time until you run a current through it. And so this is obviously something that would be very useful if it worked on a CubeSat, because you could you could get a lot of the benefits of solid propulsion without a lot of the drawbacks. Unfortunately, the electric load that this provides is very unstable, and that drawing maybe it doesn't quite do that sort of configuration justice, because it doesn't quite burn flat like that, where you're going to see more of like a shape where the point nearest to the cathode is going to be, you're not seeing a flat burn, basically, is what, and additionally, it's difficult to mix and package, as we're finding out now. So we haven't actually done any firing tests with this. We're hoping to kind of work towards that in next year, because we're needing more in terms of power supplies and actually getting all of the ingredients to mix this up. And then also to the mixer itself, because the mixer itself usually uses a vacuum system that also pulls all the air out of it as it mixes it. We don't have that because it's really expensive. So, and then additionally, we've been working with steam as a propellant. So our industry partners here have a commercial water-based unit that heats the water and then expels it as steam. So like I had said in the cold gas slide, like that, that makes your specific impulse increase, and then also increases the thrust that you're able to get out of something like that. So determining the integration necessities, that kind of thing, is a little more challenging than we expected. 20 watts, even, that's low for a propulsion system, but as of talking with some other people today, it's like, well, 20 watts is the whole power budget of Golf T. So that's even with that, it's a little much. So we want to do more simulations and more modeling to determine what the sort of feasibility of that is. So some of the challenges we're facing, again, power generation, like I've said, the largest 3U panels, we can get around 20 watts. And then so we're also powering whatever else we're using on the 3U, and we're maximizing that power budget as it is now. So adding on propulsion to that is probably going to take something more like a 6U to actually do that, and we're not quite sure what the status of AMSAT's, I guess, whether we'd want to actually go to a satellite that large without going to first to 3U. But these deployable arrays are an option, so just something to think about. And then also safety. We're generally a lot less safety averse than like actual commercial missions, just because even if the propulsion system doesn't work, our mission really is doing communications. It's not meant for actually proving out the propulsion system. So we can help a lot of distributors get flight history without ending up with a lot of, I guess, risk to us in our mission, unless, you know, it explodes like it did on AO40. So, so kind of in conclusion, you know, we're trying to get more people to help out. So if you are interested in sort of AMSAT's propulsion development, we could use your help, and I hope you found that interesting. So that's sort of the state of things right now. So thank you. There's a question? Sorry.
When you have a Cubesat in orbit, which is a more important or significant variable, the specific impulse or the thrust?
It depends on what kind of maneuver you're trying to perform. So, like, generally, higher thrust systems are more efficient in performing orbital transfers, because when you fire, there's an effect basically that when you fire at periaps, you want to be putting as much energy into that burst as possible, and that's how you end up getting like a Hohmann transfer, right? That's the most efficient transfer you can do. But for collision avoidance, that kind of thing, perhaps it just matters what you're trying to do with it. It's not necessarily universally a specific impulse or thrust is more important, I would say.
Do you have the numbers for the steam one? Excuse me, do you have the numbers, specific impulse, and so on for the steam one at this point?
Isn't it like a 106?
170.
Yeah, yeah,
170 specific.
yeah.
Thanks.
And like 20 watts. 20 watts over the lifetime of an orbit, so, yeah. Jeez. I got 5.
Have we done any modeling, you know, the ion thrusters, I guess, as a very low Newton force, if to use one of those for a orbital transfer from, say, like GTO to GEO, how long would that take? And is there enough, because doesn't it also use some sort of little material that it burns, creates the ion? Is there enough in there to create that transfer?
We haven't really looked much into those types of systems, just because of the cost. We sort of wrote those off to start with. But I know to do those, that's a multi-year kind of thing where you're going from. It really helps to get as high of an orbit as you can before starting something like that to begin with, because I mean you're reducing the amount of energy that you're using total by I guess squared, right, as you go up. So the higher the orbit we can start in, the better. But yeah, I think that would be a very challenging mission, and also those kind of things to model are. We're working on that now, because that like I had said, that simulation, that the trajectory simulation that I had written was not the most efficient. So trying to do long-term transfers like that really was taking I would let it run overnight and it still wouldn't be done doing that kind of simulation. So that's why we're working with some more powerful simulation tools now to try and do that.
I'm Jeff. I'm also on the propulsion team, and we brought some demo hardware to look at so that you can get a little bit of a physical look at what it is. Just to kind of add on to that, you know, we don't have anything that you could call a requirement, right? Because we don't know what orbit we're going to go into. We don't know exactly how big the satellite's going to be. So we've been doing a lot of what-if kind of things. And certain propulsion systems are really effective for certain operations. For example, collision avoidance. You don't really have to move very far to avoid a collision, especially if you can get a couple days in advance. But you may only have a couple days, so you need to be able to turn it on and go right now, which is where something like that electric propellant is pretty compelling, because that's something that I can energize and turn on in less than a second. Whereas the steam propulsion, that might take 10 hours in order for it to heat up and be ready to fire. An ion system, you can turn it on right now, but it might take it 6 weeks to get out of the way, right? So all these different propulsion technologies that we've looked at up here, they kind of have their place is where they fit, and is there just a single one that's going to work? Well, we'll see. It may be a multiple of things that ultimately do the missions. But the missions that we see as a minimum that we want to accomplish is we want to be able to raise the orbit to something higher to give us a better footprint so that we've got an easier job of communicating with them for the members that are on the ground. We want to be able to do collision avoidance, and we want to be able to do deorbit. So if we can find some combination of thrust systems that does that, then that's great. The steam system looks like it's one of the best because it has the ability to carry a lot of propellant. And we should have probably even emphasized more the issue of safety. Depending on who's providing the ride, we're just a little piece of ballast on some bigger payload. And they're not going to tolerate risk in that little payload. So even something like lithium-ion batteries on board gets kind of scary. And certainly something like hydrazine propellant is no way, no how. But they won't even allow us to put pressurized gas on. We can go up to 99 PSI, at least for some rides, as a maximum. And if you've only got 99 PSI to work with a gas, that's not much in the way of thrust. But what the steam system brings to us is we can put lots of propellant on because it's just water, and it's powered by the sun. So as long as we've got sunlight, we can charge up that thermal capacitor, and then we can propel the satellite. So yeah, there's a question. I guess I should give you the mic.
So when you're considering water as a propellant, have you thought about electrolysis and then burning the resultant oxygen and hydrogen?
So we have kind of talked about that, and maybe, I don't know, Jeff sounds like he wants to say something, but yes, yeah. I mean, the problem is just whether it's more efficient than just heating the water itself. So that's really what we have to consider. But
Yeah, there are demonstration systems that have done exactly that, and it's certainly in our consideration matrix of systems that we might want to use. And that's something I guess I should emphasize is we haven't made any decisions that this is our system. What we're trying to do is get experience with all of these different things to find out kind of what their advantages are and maybe what their risks are that aren't on the data sheet, right? I mean, data sheets are there to sell you on something. They usually don't have a column of, oh, these are the things that could go wrong. And that's one of the reasons we want to get hands-on experience with these things. So we brought some stuff over here so that you can look at it. What we have is, and you can come up in a few minutes, we have, this would actually be something that might be a flight unit right here. This is provided by our partners at Thermosat. This particular one was designed for on-orbit assembly, so it's got a little box on the back of it that allows you to plug it in and pull it out. But it contains a propellant tank. It contains what we call the thermal capacitor, the object that gets hot, and the thrust unit itself. And this one can be fired. There's a little cutaway that shows the heater and shows the thrust chamber here so you can see it. And then there's a 3D printed plastic version just so that you can see what the channels look like and how it flows. And for me, this was a good one to kind of get a picture of what we're talking about. With propulsion, it's easy to think about big thrusters and things. That's not what we're talking about here. These things are very small to go onto a Cubesat. Then this is an actual demo box that Thermosat brought along that is charged and ready to go. But only Cameron knows how to operate this, or Troy, our partner. So we'll actually, I believe, fire this for you in a few minutes. It's ready to go. So Cameron, if you're going to throw the switch, you got to come down here.
oh, okay.
And then we started this whole adventure I actually was at one of the previous symposia, and this unit was being demonstrated at the symposia, and I thought, well, I'm an electrical guy. That looks like fun. I'll join the propulsion team. And then I found out I was the propulsion team. So we did some testing with this. It is an effective propulsion system, but it's got nowhere near enough impulse to do an orbital transfer. In fact, once we started working with it, we're kind of like, well, what is this thing good for? When we talked to the manufacturer, what this was designed for and used for was for orbital maneuvers between like a fleet. So like you launch two satellites together, they need to fly apart, maybe come back and reassemble or something. So you're only changing, a few meters per second at most. This can do that. The concern with this was, what kind of electromagnetic emissions does this produce? So that's why we got a hold of one. I made some special probes for measuring things like BDOT and stuff like that, that people that do electromagnetic compatibility are familiar with. And we tested it, and yeah, it produces a lot of RFI. So that's another trade-off that we didn't really talk about here, and that is, some of these systems, if you're firing the thrust system, you're not going to do anything else, because it's going to generate so much electrical noise that your radio is going to be useless. That's not bad if the thrust is only going to happen for 5 seconds. But if we've got a thrust for 6 weeks to change an orbit, that's not really ideal. The advantage of this thrust system here with the steam is it's electromagnetically silent. So we can operate that thruster, provided we've got electric power, which is just a matter of how many solar panels you want to buy. We can operate that while we're doing other things, like operating a radio. So that's another trade-off. So Cameron, do you want to show the box? He's got the instructions here, so hopefully it's in the right order. So it'll be charging. We may do a different break and actually, because it came in only partially heated, so it's charging right now. But it is loaded with propellant, which is water. So in the time I would say that's yet to go, come on up and get a closer look at it and ask questions, and we'll answer what we can. And then when it's ready, we'll let you stand back a little bit and we'll throw the switch. So.
You're talking about 30 minutes or better?
About how long do you think it would be till it's ready? So maybe 5 minutes. So anyway, so come up and take a look.
I would like to add to the whole overall purpose of this is Jeff Vollen mentioned that they weren't designing to a specific mission, and that's true. Ascent is, call it the skunk works, but they're there to look for new technologies to help us with our Cubesat program. So it's not geared toward any specific mission. It's geared for what's best useful for certain different missions, or you know, like he said, there's a variety of ways to do it depending on what you want to do. So that's what their job is to explore.
All right, next up from Alabama, Jim McCullers is going to talk about OsTrax.
Okay, just make sure. I have to put the microphone into short guy mode here. My name is Jim McCullers, WA4CWI. I'm from Birmingham, Alabama, and I'm also a member of the AMSAT engineering team. I've been a professional programmer all of my career, working on operating systems and communications. I'm also the author of a app called SIGTRAC, which is used by the RF locator guys, fox hunting, and it's sort of used around the world. And the reason I included it is just wanted to let you know that I've got a background into working in amateur radio areas. Below is something that I cannot believe survived through history, and it's a copy of my novice license. And there is no reason that should exist, but it does. But it does show that I was officially licensed in September of 1961, which, if you want to do the math, you know, it's easy. I can't avoid it, okay?
5 years old.
Yeah, I was 5 years old. Oh, younger than that. But the interesting thing about that is 3 months later, Oscar I was launched in December of 1961. And I can recall, as a kid, being in ARRL, getting QST, and reading all of the articles about Oscar I and satellites and EME. And as a young kid, it was like, I got to do that. Well, it took a lifetime, but here I am, okay? So, very interesting is these are two QSTs that I came up with in January of '62 and February of '62. If you ever get the chance, would like to read up on Oscar I. They're very good presentations of what went on then. And, whoops. One of the things they did not talk about in the articles was how they tracked the satellites at that time. I know they were using radar because one of those facilities was near my hometown, but for amateur radios in the early days, tracking the satellites had to be most interesting. So I ran through and was, with the help of a couple of people that are here, came up with some of the earlier satellite tracking programs. And these are back in the beginning of history. I love Oscar Locator because it is the beginning of a graphic approach to be able to visualize an orbit. And you see a lot of different names there, and there were a lot more, and there's several duplicates on each one. All were based later on the element of the TLA, the two-line element, which came out in the 60s and 70s. Now, satellite tracking requirements: one, you need information, operation, and then the result of that, obviously, is your communication. Information along the lines of what's the name of the satellite, where's the satellite, where's the location of the satellite, the paths of the satellite, the communications tracks. Operation is how do you control your radar, your radio, and how do you control the rotors? Early days, it was all manual. It was 6 hands all going at one time. So it must have been very interesting. But as time progressed, more satellite programs came out. Whoops, got ahead. When I got in, after experience in programming, experience in working with mobile devices, when I got into doing satellites, I wasn't happy with some of the software that I found because I thought it was a little bit too cumbersome to use. It didn't fit my needs. I was always having to get another third piece of information in to do the satellite. So I was a bit frustrated, and the mind says, there's got to be a better way. And then one day I said those famous words, how difficult could this be? I forgot space is hard. Anyway, after several years of effort and the help of some very nice people in this room, able to give you the introduction of OsTrax, as I call it. Others have called it OsTrax. I really don't have an argument. Orbiting satellite tracking for the next generation, which I believe is going to be a new generation of satellite tracking programs that solve some of the problems of what we've seen in the past. And this is a working screen, okay? And we'll be talking about several different elements on this screen as we go along. But the presentation is new. It fits the modern paradigm of what software should be, what a desktop system should be. And I believe you're going to find it's far simpler to use with far more information and far more ways to get to the information. Speaking of information, of course, to get anything done, we've got to know where the satellite is. Today, we use Keplerian elements, or KEPs, from AMSAT or OsTrax, and in OsTrax, you can define your own. If you have a satellite that just hasn't been put into the system yet, or if there's an error, it does happen in the KEP files on occasion. Keplerian files are automatically updated. As a user, you set a parameter that says every so many hours I want you to go out and check the KEPs. When the KEPs come up, it pops a flag up that we'll see a little bit later that tells you, hey, you want to go update your KEPs, you know, somebody has changed something. The same thing, satellite profiles, no more manually entering satellite information and trying to get everything in order and keeping up with it. OsTrax will maintain a repository that has all of the satellite information, and that satellite information is updated just like the Keplerian files. If a change is made to that repository, the next time your program checks for changes, it will flag it and you can go and update it. And that would be like if frequencies change or if a new satellite comes into orbit and we get the comm links and everything defined for it. Same update process as the KEPs. This is just highlighting some of the features, and I'm pointing out controls. All controls for operating the radios, operating the satellite passes are well defined. They are also giving indications if the control is pressed or not, activity indications. And they're laid out in several different areas we'll discuss in a minute. At the very top, you will see there are some bars. These are the dynamic elements, things that help you know where you are in the current satellite pass, to give you a little indication that if you better start wrapping things up or you're about to lose the satellite, or where the position of the satellite may be in the sky. The system is broken into basically 5 different areas, okay? And we're just going to step through those very quickly. I broke them out just so you would get an understanding of what they are. And we'll start with the pretty stuff, which is the satellite tracking map. As opposed to some of the maps which try to show the curvature of the Earth, I decided and I settled on a flat Mercator projection, which is now common in websites and mobile apps. So everyone is more familiar with it. I like it a lot better because it shows the satellite track a lot cleaner, okay? Also, the satellite footprint doesn't get distorted trying to cope. There's no such thing as a perfect projection of a globe or a sphere onto a flat surface. So the Mercator is just one of those. It has become very popular. You will also notice that the satellite track is showing in different colors. Those different colors indicate the position of the satellite within the pass. Red is the distance behind the satellite or the path behind the satellite. The green section that you'll see shows the active part. This is where the pass is visible to you, and the orange or kind of amber shows where the satellite is, the path is going next. Now, to those who may have red-green color vision, there is an optional parameter that you can change that, and you can change the colors, and we're still working to define all of those colors and those transitions. At the very top, this is the information area. This gives you current times very upfront, so that if you're trying to do your manual logging, you don't have to go looking for the clock, both local time and UTC. And then you've got the satellite position indicator, which gives the current azimuth elevation, the max elevation, and then the countdown clock. Prior to a satellite getting to AOS, it is counting down the number of minutes or seconds, hours, whatever, to AOS. Once it goes AOS, it changes and counts down to LOS, so you will know how much longer you have left in the satellite pass. Oh, I'm sorry. I got distracted. I'm standing too close. I've been looking at these slides from across the room. The top two, the top and the bottom, are control sections, okay? The top presents a menu system, which is common for just about all apps now. Information in the middle that shows what we call the current ground station name and also grid square. And there's also an information area over onto the right of that. The bottom are hardware controls to control if you need to connect or disconnect the radio or the rotor, or if the USB cable unplugs and you need to reconnect back in. So those are the control areas. And then starting with the menu system, the very first is the preference. And you'll notice on the preferences, we have general preferences, the map, which controls the physical characteristics of the map, the pass, which we'll be talking about a little bit later, radio and rotor options, and then Doppler, to be able to set your Doppler changes by modulation type, like sideband or CW, FM. Two parameters on those sets, how often is checked, and then the delta that is checked before it decides to update the Doppler. So as you're going along, you can adjust the Doppler numbers as you wish. Now I'm going to see if I can get this to work. Okay. There we go. Okay, I want to give this just a little bit of an illustration of what you can do with the preference changes. And we're going to make a few changes here. We're going to go up, open preferences. We're going to turn on visual icons. We're going to change the map to gray, make the pass wider, add a couple of footprints for locations of our friends, and turn on the day-night terminator, and there you go. The system has reconfigured itself to meet whatever your operating requirements might be at the time. Also, you'll notice over on the far right, those are the visual icons. Again, it is an aid to those that might not have a little problem seeing different colors or might want a little bit more visual recognition of what's going on the system. Again, it's all optional. Okay, there we go. Whoops. Oh, okay. The next one we're showing, this is the CAPS. And in the CAPS, we have something called Pass Predict, and I'll talk about that later. Status, and also the ability to update the CAPS and enter user CAPS or user communication links. Like I said, we define communication links. We can miss one, or you may have a new satellite that comes up with a new link and you want to add it in, or something about a satellite you want to track that maybe is not amateur related. That can be entered with the CAPS. You will notice up in the upper right-hand corner, CAP update available. Okay? That means the system has gone out and checked, and there's a KEP or a satellite profile update available. And this gives you the opportunity to, once again, show exactly how that operation works. Whoops. Let's see. There we go. I'm sorry, I went the wrong direction. Go up to the KEPs. We're going to check the status. We see OsTrax needs to be updated. Come down to do an update. You'll notice the notification goes away and the KEPs have been updated for OsTrax. There's also a way to force every update, and you can go up and double click. You didn't have to go to that status. That's just another feature that I thought it would be easier to demonstrate here. Again, on tracking, we can track the sun, the moon, satellites, and also user tracking, which is a diagnostic tool that might not be used by everyone, but it allows you to manually step through the paths of a satellite. If you were doing experimental work, trying to determine the orbit of a satellite or something is going wrong. But those are, again, just the options. The left-hand panel is the device panel. All of the devices are in the left-hand side, including the satellite, the radio, and the rotor, pardon me. And each one of those has its own controls available. This is how you select a radio. You go up to the settings, collect radio selection, 2 radios available, 1 or 2. You come out and you pick out the radio, define the comlink, define the baud rate, and then the system reconfigures for whatever radio that you selected. These are the radios that have been tested. Okay? Just about everything that's satellite related, some that are not. Radios without satellite mode can be selected as transmit only or receive only. As a safety prevention to keep someone from trying to do full duplex on a half duplex radio. It will get updated, but quite often it will change frequencies where you don't want it to be changed if the Doppler occurs with the transmit button down. So the system restricts that. On the rotor, it's the same thing. You have the capability of selecting a rotor. Also, you set up the comlink to it. Everything is done in OsTrax with comlinks. And also, you can define the characteristics of the rotor, okay? And how you want it centered, the rotation, maximum degrees, maximum elevation, or anything like that. Obviously, you have to know something about the rotor before you define it. And these are the list of the rotors that have been defined. Just about all of the rotors, and I've tested with each and every one of these. So there have been some hours playing with different rotors to make sure everything is working correctly. Just to let you know, I have been using pieces of this for 3 years in my own shack, even down to when I was hammering in some of the definitions before that got started. So a lot of hours have been spent. Okay. Over on the right-hand side is the pass. Everything in OsTrax is based on a pass. And what a pass is obviously when the satellite is passing over your ground station. Okay? What you can do with OsTrax, and sorry about that, and the passes, is you define satellites that you are interested in. Then the system lists the passes for a given time period. It automatically segues it through those passes. And you can use or control that with the controls if you want to skip a satellite or if you want to extend the pass on a satellite. Or in the cases of people that have been using for telemetry, you just configure the entire thing with one satellite, turn it on, and it will track every pass of that satellite to gather telemetry. So those definitions, again, are user definitions. The top section is what we call the current pass. This is the guy that's highlighted in green, okay? That is all of the satellite information, the current orbit information for the satellite. Also lists the current communication link that is active for that satellite, which can be changed. Whoops. Okay. What we're going to do here is show a little bit of a demonstration of a satellite making a transition from not active to active. If you look up at AOS, it says they're 2 minutes and 8 seconds until the satellite goes to AOS. You can define a parameter that's AOS pre-start that says this many minutes before AOS, I want you to start tracking the satellite and moving the rotor. That way the rotor has a chance to get in position, be at the satellite by the time. Now, on this case, I'm using 2 minutes as my rotor tends to be slow, and I've gotten accustomed to doing that. So, watch what happens up in the column upper right-hand side where it says AOS. As it counts down, okay, it transitioned, and never do a demo. Rule 1, never do a demo. That was supposed to move over to, well, no, I'm sorry, I've forgotten this slide. I apologize. Let's roll it again. Okay. What we're going to see is that when it transitions, the radio side comes alive. And the rotor, okay? And the device sides come alive. When there's no pass going on, this side will essentially be dark, just to let you know there's nothing happening. But you can run the system in a continuous mode. Okay? Again, we're going to show a quick video. This is what happens at the end of a pass. We've got a few seconds left, and now we're going to extend the pass. Okay? Here we go. When the pass ends, we just bought ourselves another 3 minutes, and that is another optional feature. And that's useful for that pass that, okay, the pass is over, but oh my gosh, signals are still coming in. I want to stay here for a while. And there's also a delay parameter at the end of a pass that that will say how long the pass remains. Okay, this is an example of being able to change the communication link during the process. This is the comm link that's active. We're going to come over. We're going to change the comm link, change the definition to beacon, and you'll notice that the radio gets reconfigured now and is receiving the beacon. And then we'll go back and we'll recheck it. We'll change it back, and then it reconfigures the radio. So it's instantaneous. And it shows as a status area down here that shows the comm link has changed. Okay, we talked about upcoming passes. Here are the passes. These are by definition. You can define a ground station, and under the ground station, you can decide any number of ground stations, and then under the ground stations, any number of satellite groups. Okay, so that gives you that definition. And then this is going to illustrate how to delete a satellite out of the satellite group. We're deleting both of the HAIDs, SO-124, 125. You will notice they're now gone out of the group. And just for the heck of it, we'll go back and we'll put them back in just to show you how quick. Up here, there's a wildcard, so you don't have to know exactly how to spell it. Now they're back in the satellite pass. And so you can add or define passes as you go along. For the sake of, I'm getting signaled I'm running short on time, and I knew this would happen. Additional features, and there are more controls on the pass that I'll be able to talk to you or be glad to talk to you about it. Here's some additional features. Contact logging. It will automatically set up a log. We began, except I did forget there's one more thing. OsTrax is available, will be available for all 3 operating platforms, and it will have the same user interface for all 3 major platforms. Windows, Mac OS, and Ubuntu Intel. That's as far as it's stretched out. And we'll have to do some research into that because I'm not sure exactly where the limits are on the base system. So yeah, Burns, I will look into that. Okay, I got the message. Anyway, introducing OsTrax, orbital satellite tracking for the next generation, coming to your space soon. It's in the final stages of development. We're going through and just running punch lists now, getting ready for marketing. I will say the 3 different operating systems, each will be sold separately. We're also working on pricing at the moment. Hopefully for availability is going to be the very first of the year, and we'll be putting that on the AMSAT bulletin board or in the journal. I would like to say thanks to a whole bunch of people in here that I won't call out by name who loaned equipment, gave me advice, punished me on occasion, and have become great friends. Also, I am looking for a few more beta testers if you're interested. I need some people that really do a lot of operating to help me wring out some of the final bits and pieces. So, any questions?
Would you consider Raspberry Pi?
I'm not sure if this system, the base system, will run on Raspberry Pi, and that's a little bit about what Burns is talking about, okay? And I just haven't explored that, but I will. But I have to learn, this is based on a base system, and I have to know where their limits are, okay? Yes?
Will you interface with the SatNog's client?
That is not in the current. I'd love to talk to you if you know a need, okay? I mean, there's always version 2. Version 2 is already being worked on as far as futures, so at the moment it doesn't, just the basis of the system I started with, but talk to me this afternoon, okay?
This question is from Peter, MM9SQL in Scotland. He asks if it can communicate with any other applications passing frequency and satellite information for external logging programs, or if you have any plans to do that in the future, so that it could pass the frequency and the satellite directly onto logging programs.
That came up yesterday, okay? And at the moment, there's no one single interface. There could be a way, if somebody really needed it, you can configure the radio to an SDR. That will be a published spec, EasyCom for the rotor, and you could do that. But I don't think that's what he's talking about. But I was having that discussion yesterday afternoon, and again, always version 2. I need something to do at midnight, you know.
All right, thank you.
Thanks, Jim. Good presentation. I happen to have the benefit of helping test this for a while. The thing I want to note is you showed support for SDR Sharp. That's almost relevant to Peter's question because in talking with Jim early on, I said, if I can't hang a SDR receiver out there and have it controlled along with my radio, that's kind of a non-starter. And so he did from early on built a really nice plug-in for SDR Sharp. And so it uses a virtual COM port. So he has an output via COM port.
Yeah,
where
right.
you just select the SDR. So I would suspect that would let somebody hook the info because he's passing to SDR Sharp, name of the satellite,
Right.
the frequency, the mode, and that may be it. But I know it wasn't done with logging in mind, but that's a very
Correct.
important interface
Yes.
to know that works really well. So you can have a completely independent receiver. And it's pretty versatile. The other thing is the multiple session thing. You know, some of us are accustomed to running multiple radios or multiple rotors and SDR in the shack, and it accommodates that through more than one session at a time because you can configure them completely independent of one another and control lots of different hardware. So I have in normal operation one set of things hooked up to an SDR receiver that's just running through a whole bunch of different satellites and, you know, kind of on a received telemetry mode, and then others actively tracking with rotors, you know, to either work the bird or specifically put some gain on a telemetry bird. So it's very versatile.
Yeah, the SDR plugin will be available on our on the site when it comes up. Also, the SDR protocol will be published. So that's just a very simple protocol I put together, and we're going to publish that for anyone that wants to, you know, use it for their own benefit. In fact, it is written, it's just not yet up on the test website.
All right, thank you very much, Jim.
Thank you, sir.
All right, next up is Andrew Robinson, KE3 WDW Fox Plus Mechanical Layout and Design. I keep trying to use a trackpad,
Yeah.
it's disconnected.
Sweet PowerPoint.
Just a little admin note, we are live broadcasting this over the internet, and so when we get to the question part, if you'll raise your hand, I'll slip up behind you, hand the microphone, that way the audience on the internet can hear your question as well as the answer from the presenter. Thank you.
Right. So I believe I have the honor of being the person between you and a break, so I apologize for that. Don't hold it against me. But my name is Andrew Robinson, K3WDW from Littleton, Colorado, by ways of the Philadelphia area, so hence the 3 in my call. I am the mechanical design team for Fox Plus, the only one, so but I put a call out there for other knuckle-dragging mechanical guys like myself. If you're interested in helping out, could really use some help bringing this guy home and extending it to follow-on platforms. But wanted to throw together some slides to talk a little about the Fox Plus, specifically mechanically. So no hard questions about RF or electrical stuff. I won't know probably, but I will walk you through some of the challenges that we've had for the Fox Plus, putting it together, and have some pretty pictures to show you. And I actually do have some hardware. So if you like hardware, we can do some show and tell as well. Just an overview of things I'm going to talk about, but let's get into it. A little quick overview of what Fox Plus is. If you're not familiar, probably everyone is. It's a 1U Cubesat, so think, you know, Beanie Baby display case. In LEO, when we get into flight and in orbit. But the idea is, could we leverage some heritage AMSAT electronic guts, right? Things that we've flown before, flown in the past, have a lot of heritage, a lot of knowledge on the design, specifically the LTM, and make a little bit of a Frankenstein with off-the-shelf hardware. And the idea is, hey, if we can leverage some off-the-shelf hardware, this might turn into a little bit of an easy button. We could maybe start to, pseudo mass produce these things, maybe have some of these on the shelves, so whenever we do have opportunities for a flight, it would be a pretty quick turn to get it manifested and out into orbit. So the block diagram there on the left, you might have seen before if you call into the Wednesday calls. Mike usually shows this at the beginning of the Fox Plus piece. The stuff on the right is mostly that heritage stuff. The big box on the left, which is listed as ISIS, not the terrorist group, but it's a company in the Netherlands. That's their electrical power subsystem that we're leveraging. So the hardware, I mentioned ISIS, really innovated solutions in space. And I would typically call it ISI space. It's a little bit more of a mouthful, but it's not saying ISIS, so it's a little bit easier for me to say. We have a couple of things that I have some pictures for on the right that we're leveraging from ISI space. The main thing, that 1U frame. Antenna system there on the right, so that's a 2 meter and a 70 centimeter whip antenna that curls up inside itself and then will get deployed once on orbit. And the bottom is really that EPS system. Maybe hard to see, but that's the battery pack on the right, and the PIU, the integration unit on the left, a board that we put in our stack. Not shown here, because the website doesn't have really good pictures, is the solar arrays. So six panels, one on each side, and then a solar array on the top. The highlight here, and a lot of the struggles and why I have a lot of gray hair now, is that frame. Very particularly how it stacks up. It's actually 6 pieces. The black anodized pieces on the ends, those are 2 separate pieces. And the clear anodized might be hard to see, but those pieces there on the top and the bottom, they call their ribs. Those are 4 individual pieces. And this baby really stacks up on those ribs, sort of like you see here in the picture here from ISI space. But it's a single M3 threaded rod, stainless steel threaded rod from the top to the bottom, through a hole in the bottom and then the thread on the top. And so you can really just, like a hamburger, start stacking your boards and your guts, and compress them in so they're nice and stable. And that's how this goes together. We do have, I think I might have mentioned on the last slide, hardware for really 2 birds, I believe. I have a set of a lot of this, so I've built up a lot of the stuff at home and making sure that I have a good mechanical fit. But the idea would be, start building these things up and have them available, ready to go. So let's get into it. So those are really the last real pictures. I think most of the stuff you'll see is from Inventor. So we use a program called Inventor. It's our 3D solid mechanical machining or mechanical design software. If you're familiar with SolidWorks or Creo, very similar, just by Autodesk. It's a really good program. And so what you see on the left is purely out of the model. It's that full stack up. And you can read through on the right. Hard to see maybe with the arrows exactly what is what. So I'll walk you down through the stack up. That's the ISI space 1U frame. They're in black and partially the aluminum color. The top piece is that ISI space power unit, the power generation unit. We have a couple of our own design things. For instance, the ME204 power signal adapter, which I will get into. And then those 3 that we all know and love very well for the LTM, the IHU, the ICR, and the RXTX. We have a mechanical adapter that we designed, more on that in a few slides. And then the battery pack, and all the way at the bottom is the antenna. So that's the overview of the layout. So as I mentioned, the integration challenges were many and pretty challenging. The ISI space comes with its own hole pattern, non-symmetric, kind of funky little hole pattern that is nothing at all like what we use in our standard, what we call the Fox ME113 PCB layout. 79 millimeter hole centers, both the same, kind of centered nicely on the board. It's a real beauty, not unlike the ISI space, is these dark blue dots on this layout. But I put this together to really show, and it might not be very apparent from this, but they're not close enough where it could be an easy, hey, let's just make a slot instead of a hole. but they're not far enough away to make it really easy to put an adapter in between them. And so we struggled with trying to move things around. How could we line this up so that we could use the boards, the LTM boards that we have on hand, and integrate it into this ISI space whole schema, which is really challenging, especially with unable to move too far in this kind of plane that you see on the screen, and ideally not wanting to take a lot of vertical space because we have a bunch of boards to get in there. The idea is of maybe running a payload in the future. We were cognitive of trying to minimize how much space we have vertically as well. So we came up with really two courses of action. COA 1 is just adopting the ISI space mounting schema. And so the idea would be, hey, I can build new boards that look a lot like the ISI space layout, this 92 millimeter by 96 millimeter with that funky non-symmetric hole pattern. And then, right-click, paste my electrical design on those new boards. Obviously, a little humor there with the mechanical guy. It's not that easy. But that would be, a concept of now having to respin or redo boards on this new layout. This was what I would call the easy button mechanically. You see the pros and cons there at the bottom. Very easy. We could really just leverage what you see here in the bottom left of how the folks at ISI Space anticipate this one U bird coming together. All the hole patterns would be the same. We can just build this the stack of pancakes and put it together real nicely. Very space efficient. You kind of use all that vertical space that we have available. The cons really hurt though, obviously, having to kind of redesign, rebuild a lot of those boards, having incompatible kind of backwards compatibility going away of not being able to take this new ISI space mounting schema, and we no longer be able to use those on other boards or designs that use the ME113. So understandably, it was fairly hard jump considering some of those cons. So we went back to the drawing board and came up with COA 2, which was a mechanical adapter. And so what you see here is a export from the model, from our inventor model of this adapter design. And it's essentially it's essentially this, right? So around 95 by 95 millimeters. I want to say at the thickest part, it's maybe, 10 or 11 millimeters thick. But the idea here is on the bottom of this, so kind of what you can't see, but on the bottom face, it has the whole pattern for the ISI mounting schema. And the top is the Fox ME113 mounting schema, which is what Golf is using as well. So it's also the Golf ME113. And so, obviously the pro here is being able to use those existing boards. Didn't have to respin, redesign any of these boards. Had them on hand, kind of an easy win there. Was a bit complicated to integrate as you do this stack up, having that mechanical adapter in there. And the big one really is we lost a lot of space. Right now I have room for this this piece of aluminum. Now it's not room for a board. So somewhat limited on what we could have used for additional payloads and things like that. I do have some potential concerns with shock and vibe. I'll touch on that in a better view that I have in a slide or two. But this, for being a very small piece, was fairly challenging to kind of come up with and design, make sure all alignments were correctly. Such is the case, I put a bit of an Easter egg in here, and so those lightning holes are my initials in Morse code. So this thing will be flying my name here once we get into orbit. The bottom right is a three-quarter cross section, just really showing you where those holes are, the one from the bottom and one from the top, and just give you an idea of the limited space we have here. And those are 3 millimeter helicoils, so really just getting the minimum thread engagement that you would want for an M3 fastener. So it's really tight, not a lot of room to grow or modify, but we got it done, and Machine Shop has manufactured a few of these for us. So I'm not a fan of PowerPoint Build-A-Bear, but assembly process is one of the spots where it really makes a lot of sense. So I wanted to walk through conceptually where we're at on this assembly process. So we'd start again with those two bottom ribs, part of the frame, and the battery goes on first. So that's a simple counter screw or a flathead screw M3 fastener that will go up from the bottom through the battery on the bottom. We put that mechanical adapter on there, and as I mentioned before, the bottom has the whole pattern for the ISI space mounting schema, and they're threaded with helicoils, so that would be an easy process, right? You can just lock tight and torque those threads down, and we'd have a good start. Next is the stack, so the LTM stack plus the PSA. Again, same song, second verse. Now we're going from the top down. My threads are on that mechanical adapter, so I can now drive those M3 socket head screws down and torque that stack of boards down pretty good. Pretty easy to do. I've done this at home a couple times, but I actually use a big chunk of M3 all thread on these 4 holes in this configuration, and then I can just use those as guideposts to slide the boards down and the spacers. Those are little 8mm spacers, heritage design. I think Bob Davis used those for all the Foxbirds and those other designs. Perfect engagement for those QSH and QTH connectors that we're using. So that was an easy win, and it goes together really well. So this top board, I have a slide on. That's the power signal adapter board. What we found out was we needed a bit of a translator or a way to go from where we end our signals at that top board, the LIHU, to the PIU, the power integration unit that sits up top. And so this is our go-between, and hard to see, I apologize, but that's a QSH on the bottom side of that board, and then some pins that will connect to the CSKB connector that's on the PIU. So now we're able to send signals and power back and forth. I designed it mechanically, and Mike has done the wire traces and have started to play around with, see how that guy fits, but so far so good. The tricky part is when we go to the next step, it looks a little bit like magic, but that's the PIU mounted to the top 2 ribs. And in this configuration, in the magic of a solid model, that's really just floating there on nothing but those pins. So I would engage these pins on the PSA with the female piece on the PIU. And so that's where the majority of a lot of my concerns about shock and vibe is in this configuration. Your only thing between these 2 stacks is the connection with those pins. I'm not losing any sleep on it right now, but it is something I want to keep my mind on, keep an eye on as we kind of continue to mature this design. Now, fortunately, this isn't the only thing obviously holding up. We have one last step, and that's to put those black anodized aluminum pieces on the edges. And so you can see from a bunch of flathead screws that will connect those 4 ribs with the side rails. So we do have some additional structural support in there, but with any sort of weird little twistings inside this bird, might get some weird loads and load paths. So the PSA, the power signal adapter, this was that board I was mentioning before. That, as you can see on the bottom, has the QSH, and the top, these MTSWs, I think are also made by Samtech, but just large pins. Our first go around, where they were, 300, the last 3 digits is the length, and they were 300 thousandths, so 3/10 long, too long. Couldn't, I bottomed out and couldn't get a good engagement. So we replaced them with the 235s, and they fit into the PIU, gorgeously. So that bottom right is just giving you a side view of the stack up. The LIU or LIHU with the QSH, QTH, can't see in this view here, but those pins, I think 52 of those pins with that female connector that's on the PIU, what they call the CSKB, Cubesat kick board, or I forget what the acronym is, but. So some current status, where we're currently at. Got a lot of work done. Parts are being made. The power signal adapter, the design has been finalized, the mechanical design of it, so that board. There's some tweaks, for instance, that pin length we still need to clean up, but we'll get that cleaned up and released. the mechanical adapter. This bad boy was all manufactured, all machined off of just step files. So literally just kind of clicked and dragged that onto a website, an e-machine shop website, and they were able to quote it and actually manufacture it just off the STP, which was great. And in about 3 or 4 weeks, it showed up at my front door. The drawing is still in progress. We're still getting that finalized, but we do have the parts in house. One struggle, I guess, with my big fingers, getting little M3 helicoils in those little threads is quite a challenge. So maybe not drink coffee one morning and I might be able to get it done. But that's kind of where we're at with there. But all hardware for that guy is in house. All the other hardware, so a couple McMaster-Carr orders for fasteners, the spacers, washers, all that is also in house. I have at home sitting the mechanical fit model, so one of these birds sitting on the ISI space jig, built up with some dummy boards, so not real birds, just boards with has the right hole patterns, but really not populating anything special, just to see how everything fits. Solar ray blanks, I had designed a few and had a few made. I think I have a picture in a couple slides, but really to take the place of the solar rays, just pure aluminum pieces that we can put on there, fasten in there, just to give it a little protection without putting the solar rays, which are pretty costly. So don't want to use those until we're really ready to use them. And then the last piece there, so the ME202 is the top level assembly, and working to finalize its drawings with the up-to-date BOM and assembly procedures. So as I built up that mechanical fit model, took some really good notes on the right orders, the right tools, the right processes, everything I use, so refining those. So at the end of the day, I'll have a document, maybe PDF or Word document that shows exactly how we put this bad boy together. If you're keeping track of numbers, you'll see, well, there's a 204, a 203, and a 202, whatever happened to 201. That's actually the wire that you see in here, and that's actually kind of the next steps that we're working. Inventor does have some really robust toolbox for doing wire routing, and this was my first go because I knew where it was supposed to go and where it was supposed to land. And so you literally just kind of pick out the points here. I want to start here. I want it to end there. Inventor will say, well, I'll give you a straight path. And then you use these, what they call segments, these blue pieces that you'll see on the model to say, nope, I don't want a straight line. I want to follow a certain path. The beauty of that is once you get it laid out, everything is how situated, how you want. It produces a drawing for you of the proper length, the proper connectors, where's pin 1, where's pin 9, all that good stuff. So that becomes a drawing, which I gave kind of Quentin Tarantino style, going from the end to beginning. I gave that 201. So that's where we're at with that guy. So path forwards. Here is again another output from the model. Now with its clothes on, has the 5 solar panels situated as it will. I mentioned the wire routing using the Inventor Toolbox. This design does leverage those QXHs, so not a lot of wires, but there will be some wires that we need to route. So make sure that we capture those, design those, and then work to get them built. Supporting the engineering model and any tests. Obviously, that's the next big step as we go PDR to CDR. And then I know thinking ahead, but always like to think about launch. So finalizing and releasing the drawings and documents, supporting that flight model build, test and launch, and then any sort of tweaks as we think about Fox plus B. So everything picture-wise and discussion was really Fox plus A, the first bird out of the house here. But what changes, what might we need for Fox plus B, the second iteration, still using the ISI space, COTS hardware, but making any changes to the design, to the layouts, and the build for Fox plus B. And my get off the stage chart is a couple pictures. This is from my desk back at home, but that is our mechanical fit model on the left, without the covers on, showing kind of the insides. You will see there's actually a blue piece in here, might be hard to see. That was a plastic printed version of this. It was before I had the metal pieces made, and we had them, the design just printed out of plastic. and then put in some brass threads, melted into plastic. So I was able to build that stack up. And then the view on the right is those solar array covers, really just black anodized aluminum, just to keep it protected while it, so my two-year-old son doesn't stick his fingers in something and hurting something. So that's all I have for you. Appreciate the time.
I got one thing. Don't go away. Could you explain what the little extensions to the posts are at the top, if you will, of the satellite there?
Yeah, so you'll see, if you're talking about these little buttons, right? Yeah, so built into the frames, there's 2 of them, and they're just little push buttons for detect and release. I don't think I have a view. Some of my model views you might see here, so that's the same as these little buttons here. So that's just a little pop button with a spring underneath and a switch. So some of these hardware here, I'm sure it's probably hard to see here, but there's a little switch mounted to the side of the frame. So when in its shooter, in the dispenser, those things will be depressed. It gets popped out, and those will also pop out to give you indication that you've been released. And I believe, per the ICD with that shooter, that is -Z, I think. And I reordered everything so that was aligned with the ICD.
Okay, I got 2 questions. First one, the whole pattern from ISI Space, isn't that the PC-104 whole specification, or is it vary from that?
I think it's similar, but maybe different. It's very, very weird. But I'm not a PC-104, not very knowledgeable of that. But
And the reason why I asked that question is our LTM is meant as a product to assist other outside organizations to be able to launch amateur radio in space. Yeah. So if our whole pattern isn't close to what's available on COTS, doesn't that require all those other organizations to either, number one, adopt all of our subsystems, or number 2, have this mechanical adapter in between?
Yeah. This the Fox ME-113 is its own beast, right? I guess Heritage Fox design for the Fox 1s that were kind of roll drone design. So I don't know.
And maybe Burns or Jerry will answer this. Wasn't HuskySat PC-104 card that we use for LTM with the whole pattern?
The PC-104 connector, interfacing that with the CSKB light, which is another standard, right, wasn't practical. So what we did was we went ahead and used the QSH, QTH connector combo to go to that adapter board, as opposed to taking the PC-104 connector, that big piece, if you will, just to pass a few signals, essentially. So the PC-104 you're talking about is not on this. It was just simply removed from the LTM so that we could make it fit better with the ISIS.
Yeah. The PC-104 is the connector. The whole pattern is something different. Yeah. Is that a question or a statement? No, it's a statement. Okay. I had never heard of it. Yeah, so it's a connector as far as I know. But
anybody else know if PC-104 is anything to do with whole patterns of PCB? I'll show you. What?
There's a question up front. Any questions? Yep.
Maybe you said it and I missed it, but why didn't you put that top board on that same all thread going through all the other boards? I missed. If you said it, I missed it.
So you're talking about this top board?
Yeah, the top board connecting to the next one, those spacers, like you did the other 4 boards.
Yeah. So this is an ISI space board. So that has that hole pattern that mounts real nicely with the frame. So I kind of leveraged that whole pattern And everything else here down has the ME113 whole pattern.
And then the other thing was, I noticed that you did do that one thing in plastic and then you switched to metal.
Yeah.
Was it just you didn't think the plastic would be strong enough?
Oh, no, the plastic was just a prototype, just to get something done quick. We had that in like a couple days mailed to me. It was real nice. I think metal seems to be a little bit more robust moving forward, so redesigned it, rebuilt it in aluminum. Awesome.
Any other questions?
Nice work, interesting presentation. It's fun seeing it stacked together. Forgive me for the ignorance, but you mentioned the point between those boards. You're worried about what, the vibe and rock and roll test. Is it just metal pins connecting those two, and you're relying on the structure above and below to hold them?
Yeah, best in this view here in the bottom right. So there's no, the four kind of pillars that go up and down through the boards. There's no connection between this board and that board with that pillar. So this board is mounted to the top, and that board is mounted to the bottom.
And then spread. Because naivete is wonderful, right? So I'm sitting here thinking, well, why don't you make one of those, but on the other end, you kind of double adapt it so that you could have a plug-in to their hardware with ours, on both sides of it.
I did that. I had a concept that looked like that.
I figured you did.
Yeah, and it's challenging. The biggest challenge was, the original concept, from ISI Space is, down here is a through hole. It's a countersunk through hole. So you use a flat head all the way up, and then you have the female end here. Putting this in here, it got real challenging keeping track of my genders, right? Because ideally you just want everything to kind of go up, but here you're kind of meeting in the middle. Now you have something going up, but now you have two females, so now you have to have something come down. It was a lot of back and forth on how to arrange this, and then making sure that, I got to put this thing together, and so I can't have like this I can torque because this won't be here, right? But if you had the stack where you have a bolt head where you need to get an Allen wrench or something in there, you got to have accessibility, right? Thinking manufacturability, assemblability, right? So that was quite the challenge. But I do have a concept actually of more or less that thing just flipped. So once you get to the top, you can then flip it around.
And it took me a minute, but I finally saw your Morse code Easter egg in there. That's cool.
Thanks. It also is actually beneficial because there's a certain orientation that whenever I assemble this with more or less all those QXHs kind of facing me, and it's hard to see here, but like those QXHs, the QTH and QSH will be towards me, and I can know, since the nice thing about the non-symmetric hole pattern is it's only one way. You can't flip it upside down and move it around. But I know if I can read my initials that it's positioned the right way, and so I can just pop it back down. So, dual purpose.
Some of the questions that you're asking or thinking of, I think Mike Moore, he'll be here tomorrow to do a presentation tomorrow afternoon. Mike Moore is the systems engineer for Fox Plus, and he can probably answer those in more detail than I can, or perhaps the ones that Andrew doesn't know right now too.
Any more? Last call. Thank you so much, Andrew.
Thank you.
All right, if everybody can move back to their seats, let's get started. Okay. Next up is Jaime is going to talk about extending command and control for golf, greater orbit, larger footprint.
Yeah. So I'm going to talk about a protocol extension, and that I've been working on, and the current command and control setup is pretty straightforward. I mean, we have this program on the ground called AMCOM, and we simply send commands to the satellite, and it's kind of like, fire and forget. We don't know unless we get some kind of telemetry back that this actually took or not. And, it works fine. And we've been using it since 2015, okay? So for 10 years. So don't break it, I mean, So that's one of the aspects of this. And this is fine also because we have rather simple commands. And on the left there, you can see actually the Fox commands are, put it in safe mode, health mode, and so on and so forth. But when we are now working on golf, we need longer payload. We need actually bigger payload to be able to, command the satellite. And one of the main things is actually the ATCS. And in order to operate, the ATCS, we need to tell it the orbital parameters, for example. And in order to do that, we need to send all these parameters as a unit, as a single command, and then commit to it if everything comes across. You cannot just send willy-nilly, this parameter now and the other one, an hour later and so on and so forth. So that is the challenge here. And we also have way more complex systems, like Kip is working on the power system, which is, in itself a pretty complex thing, and we might need to be able to interact with those systems. So that's the background of this. So what I suggest doing is to reuse stuff that we already have. I mean, it doesn't make any sense to throw away like AMCOM that has been tried and tested for 10 years. So keep the command uplink the same, but in order to be able to get some feedback on the progression of these transmissions, again, smuggle data on the telemetry downlink. And we already have a very good, telemetry program called FoxTelem. And we happen to have like 5 bits of data in the telemetry header that we can reuse for this purpose. And that's what I've been, working on. And so FoxTelem would actually then give us these 5 bits as feedback, coming from the satellite on every packet coming down. And then I only need, this piece, which is actually down there in the left part, which I call multi-part command, which will then assemble, these commands and put AMCOM more or less in, a slave mode where actually I can send these packets. We already have some of that functionality, they are very similar to it, for the CAN commands that is already built into ANCON. But the key thing here is that using exactly the same thing on the radio, and so we are not risking any bugs and problems, and at the same time be able to extend this. So, what I'm suggesting is actually that we take the AMCOM software command that's already there. It looks like this. I mean, each command is 50 bytes, and starts with a 6-byte header, and then we have these different things, including 8 bytes of payload, practically. It's now organized as 4 16-bit values, and so that's the the plan is to actually send multiple of these to actually get more data across. And a simple way to do that is to modify this piece. Offset number 7 is already the namespace. So we have a namespace, different namespace, and for each namespace we have different commands. And this is used for, like, we can give universities a namespace, and they can actually do whatever they want and introduce their own commands without messing with any of the commands that we already have to have. And we don't have that many, so we can split it up and say, if the most significant bit of the namespace is set to 1, then this is a multipart command. And then the flight software can actually, act differently if it's a multipart command, as opposed to all the other ones. So that's the extension piece. And then we need to be able to tell the flight software how many pieces are there and which piece is this, because we can lose packets. I mean, we can actually get, instead of actually packet 0, 1, 2, and 3, we might actually get no packet 0, but 1 and 3. And we have to be able to deal with that. And so the way to do that is actually to take what we have in the software commands now as 2 bytes for commands, and we've never actually used all of that, to split it up and keep the byte number 8 the same as a command byte. So now we have 256 possible commands. Out of 128 of them can be multipart commands, and then actually introduce this sequence byte instead of the second byte that we didn't use. So the sequence byte is split up into two 4-bit fields. The first 4 parts, obviously the most significant nibble, is telling the flight software how, what's the maximum sequence number for this. And that can be a number from 0 to 15. So we can have up to 16 parts. And then for each of these parts, we have a sequence number from 0 to 15. So that's the structure, and that's basically the idea. And everything follows from this. Pretty simple. So if you're sending a sequence that has 5 parts, so we now are actually be able to send 40 bytes. This would be what would be sent. So the first sequence byte would say 40, 4 meaning the last sequence is 4, meaning 5 segments or 5 parts. And then the 5-bit thing I was talking about in the feedback, telling me how this is going, would be something like this. So I need 4 bits to acknowledge. Or basically, what I'm doing here is I'm splitting this 5-bit thing into a single bit, saying, is this an acknowledgement or not? If it is, the following 4 bits will actually contain the information. And the information is actually what is the next missing part. Okay? So if it says 0, 1, it says this, it basically means that the second part is missing. Because if the first part, which is number 0, would be missing, I would be sending acknowledgement to 0. And meaning, resend 0, please. And, and then in the end, when everything is working and everything has been executed, this acknowledgement goes away, says, okay, I'm done. And the sequence number would be 0 for the happy path, everything working fine. But I can also smuggle an error message, into those 4 bits. Hey, come on, we need to use it as much as we can. So that's what's going to happen on the wire. How does this look? I mean, this is a simple sequence diagram of a transmission, and what I'm talking about here is actually the first part. If you read this from the top to the bottom. And the 0, 0 at the top is coming from the spacecraft down to the ground station and saying 0, 0, meaning I'm not in the middle of another transmission. So basically I'm waiting until everything is clear in the spacecraft. Then I start to transmit, in this case, 4 segments or 4 parts. And I just send them one after the other. There's no reason to wait, because the telemetry is coming down, every 7 seconds or something. So I can send seven parts without waiting. If I would be waiting, I mean, I would send and wait for 7 seconds, send and wait for 7 seconds. I mean, that doesn't make any sense. Let's be optimistic and say, okay, everything is fine. But of course it isn't. So, but if it is, then we will get back, the acknowledgement saying the next segment is number 4. The ground station knows that, I don't need to send 4 because I mean it's only the 3 is the highest one, so it's one above what the last segment is. So I'm done. And then on the spacecraft we can execute that command with all that payload. And in the end, when everything, in the next round of telemetry, I will get to 0, 0 again. So we are ready to send another command. Okay? Pretty simple, right? If it fails, then the same sequence. I wait for a 0, 0, blast these 4 segments up. And instead of getting a 1, 4, meaning everything is fine, I get a 1, 2. Oops. That simply means that the lowest number part that is missing is number 2. There might be, 3 might be missing 2. I don't know. But because I only have 4 bits, right? So I resend, segment number 2, meaning the 3rd segment. And then it comes back with 1, 4, saying, hey, I'm good. And this can be executed on board. Make sense? Really simple, right? So, so then what I did, I sat down and wrote down on paper the actual, algorithms for this. And in the beginning, it was really simple, okay? And then I began to think about, what about this case? And so in practice, what this is, and you can read about this and the description of this in the actual paper that's going to be in the proceedings. So if you want to lead, want to know all about these details here. But the key thing here, though, is that we need actually two threads of execution. On the ground station. One is actually the thread that is sending the data, and then there's a separate thread that is actually receiving the telemetry. And then they have to talk to each other. And basically, this algorithm, this send MPC algorithm, will actually use the acknowledgements coming down to send these things in the order I was describing. Just trust me on that, okay? But by the way, I actually have a simulation of this algorithm that I'm going to show you because I didn't believe it myself either. So the receive is a bit more complicated, but this is actually what. Nah, I mean we can do it together, right? So yeah, but you know, but the actual each of these pieces are not that hard. But again, there are two threads of execution here. The one that is actually just, you know, getting one part to receive here on line 25, and that actually there's a segment coming in, and this algorithm also is simple in that sense that we can get these segments in any order. We just have to have memory on the spacecraft to store all of these 128 bytes. That is the maximum size of the payload. But I mean, but it can come in any order. And again, like I said, I mean, one thread is actually the one on the left is actually the main thread. But then there's a separate thing that is called by the telemetry thread that actually takes the status of what's going on, what has been received, and transmits it down. But I mean, this was great fun to work out. And okay, a little bit about the payload that we can now send. Currently, well, like I said before, we organize everything into 4 16-bit integers, basically. But there is no reason to. And so one way of doing it is actually, you know, to have these different data types. And we need them, for example, if we're going to send like the orbital parameters, those will be double precision numbers, floating point numbers. And in other cases, we might be okay with you know, like a regular float, not double precision, and then we can pack 2 of them. And so these are just you know, regular data types that we could actually put into these packets and look at them as a single payload. In the beginning, I mean, we would have to just be careful when we define these. I mean, you know, us meaning, you know, the engineering team, to actually make sure that we are not, you know, crossing a boundary on the 8-byte packets. But that's a minor thing. Okay. So and then we would actually need to define a command, and this is one way of doing that. Currently, we have a CSV format called, you know, satcommands.txt, but that's going to be really hard to squeeze this in. So I suggest that we just switch that over to JSON, which is easy, and then we will, you know, have something that's really readable for a human and easy to maintain. So in this case, this would be a command sending a subset of the orbital parameters up to the satellite. And it would say, okay, the namespace is 80. Okay, that's just a fictitious namespace, but it has the high bit set. Command number 1, the list of satellites that this applies to, you know, Golf T in this case, can be a list. I mean, Golf 1 and so on and so forth. And then I'm talking about the data file name because, say, if this is being derived from a TLE, I would rather have a program write a CSV file, and which would be written, you know, read by this and sent out, rather than trying to put this in by hand. I mean, that's you know, that's stupid. So that's one of the things that is extending this, and then of course the actual parameter names and their data type. So in this case, they're all floating, you know, 64-bit floating points, or actually double precision. And so that is how, you know, this is an example of how this would look like. Of course, we would, you know, work this out in, you know, depending on the target system on the spacecraft, what exactly we need to send. But another, you know, connection that Burns, of course, pointed out really early on, hey, are we then going to do all this by hand? But of course not. I mean, we would generate, you know, some header files for the flight software based on this input, so we don't have to do it by hand. And we, you know, when we change something, that will actually be automatically, you know, compiled into the flight software. Okay. This is basically the last slide, is it? Yeah, okay. Yeah, so what I did was, like I said before, I wrote a simulator to convince myself that this actually did work. And it was mostly about the timing, because I mean, okay, I can send one packet per second. I mean, if you think about, you know, 100 bytes at 1200 BAU, that's about a second per packet. And then we get telemetry coming down every 7 seconds. In the beginning, I did not synchronize between the telemetry downlink and the transmission, but in this algorithm I do. And that is actually a good thing. But you can see the simulator. I mean, it's just a simple multi-threaded Python thing, and it's on my GitHub. So, and there's a link there, in the GitHub to the paper itself describing this. So, this is a dangerous thing, really dangerous thing. Okay. So this is the simulator, and it's showing if I'm sending 7 parts to the satellite. In the beginning, they're all red because none of them has been received. The numbers here are actually how many times each segment has been sent, and then I have this error rate here, which is something it's basically the probability of a packet loss. So now it's set to like 10%. So there's a 10% probability that I send something to the satellite and it's just dropped on the floor. And to make this actually more realistic so we can actually see what's happened. The transmission status is shown here. And you might see actually that this color is changing every 7 seconds. Now it's green. Because there was another, and the empty set thing here actually saying is this is the 0, 0, as opposed to ACK for a 0. Okay, we'll see that. Okay, so then I started, and the simulation will start, or actually this will start when the transmission status changes. Okay, so I got these, packets coming down. Oh, all of them. Okay, and then I get ACK for 7, and I'm done, right? So this was easy, but I don't have to go that far. I'll just go up to 20, and that's enough to, to get some errors. Yeah, but okay. Now you see, these. Hey, what's going on? Come on. This never actually. So, this would always fail, when I was doing this. Okay, 30%. And, okay, yes, this, see, 0 failed. And, okay, so now you can see it's asking for 0. Say, hey, give me 0 back. And then it will ask for 4 once it gets number 0. Okay, it was sent twice. And now it's going to ask for 4 in the next packet. And it went green. Okay, so it only needed to send, these 2 packets twice. And otherwise, now it's asking for 7, saying I'm done. But if we increase this really, now it's like 50-50. And okay, 0 went through, but and this is this is going to take a while. Again, because I blast all the packets in the beginning, hoping that everything comes through. But in this case, okay, it's not too bad. It only had to send these twice. But I've seen this, have to send 2 or 3 or 4 times. But it's still lacking for 3, okay? Yeah, so, you know, like number 3 did not come through. It's been sending it 3 times now. And so this is, okay, now it finally made it. It had to send it 4 times. And so we actually don't want to operate, you know, when we have like 50% packet loss. I mean, that's basically what this is saying.
Maybe real world better, right?
I know. I mean, it is. But I mean, but the thing is, I mean, if we wait long enough, it will come through. Yes.
So you can send like 1 second, but when you have to redo it, you have to wait 7 seconds.
Yes.
For that act.
Absolutely, because I don't know which one was missing. Okay, and this simple algorithm will tell me what is the lowest number that's missing. So it always goes from left to right, so yeah, okay.
Why wouldn't you just keep sending subsequent ones until you get an act back and say, oh, I missed one, or I can skip ahead?
We could do that, yes. Yeah, because I mean we're basically sitting doing nothing for 6 seconds. Yeah, I know. And and there are so many. I mean, even though this is a really simple thing, hey, I mean, there are so many edge cases that. But that's why I actually decided to write this as a simulation to actually see it. Okay. Okay, that's it.
Any other questions?
Yes.
Very good presentation, thank you. Given the attack on satellites these days by malicious actors and malicious nation states and non-state actors, is there any plan to put encryption or other cybersecurity mechanisms in place both on the uplink and downlink?
Okay, so the uplink is already, you know, we already have a digital signature, so you cannot actually just blast it. And so it is protected that way.
Yeah, look at my paper from several years ago.
Yeah.
That's what we're doing. It is, the uplink signal is encrypted. The downlink signal is forward error corrected, but we don't care so much.
It's against FCC regulations to encrypt anything on the amateur bands with the intent to obscure other than uplink commands.
Yep.
You can't encrypt a downlink no matter what.
Right. But yeah, you can see here actually, you know, out of the 18, I mean, we have 18 bytes of actual data, followed by, you know, the signature, which is 32 bytes. So the signature and one of the, you know, you cannot either copy this because, I mean, there's a timestamp that is increasing. So you cannot do, you know, like a copy attack or anything, right? So, but it's a good point. But I mean, denial of service attack is another thing. I mean, somebody can just blast with signal and descends all of the receivers, and that would actually stop us. But yeah, good question.
Any more questions? Thank you so much.
Thank you.
All right, next presentation is an ARIS update from Frank Bauer. This will be pre-recorded. So I'm going to push the start button, and unfortunately, I don't think there's any potential for questions afterwards, but if so, we'll collect them.
Hello, everyone. I'm Frank Bauer, KA3HDO. and I really wish I could be with all of you in person, but a family emergency has kept me home. This ARIS presentation will provide an overview of what ARIS has accomplished over this past year and invite you to celebrate with us as we commemorate 25 years of continuous operations on the International Space Station. On November 13, 2000, less than 2 weeks after the first crew arrived, our first ARIS amateur radio station was commissioned, making ARIS the first operational payload on the International Space Station. The ARIS program continues to successfully navigate through the substantial changes happening in the space industry, and doing it with results-driven activities. We're embracing the substantial shift towards commercial missions with the knowledge that the ISS is planned to be decommissioned in 5 to 6 years. We are listening to our NASA and ISS National Labs sponsors on their priorities, and as a result, we've modified the emphasis of our mission as shown in this chart. First and foremost, we are an independent backup communications capability for ISS. We boost ISS crew morale through enriching youth, community, and amateur radio engagement. We continue to inspire, engage, and educate K through 16 youth in STEM via a 10-minute amateur radio contact with the on-orbit crew. And as a result, we're a workforce development powerhouse. During the 4 to 6 months prior to the ISS contact, students learn about space exploration, science research, space communications, and radio science and technology using amateur radio. And it's important to note that our youth contacts keep the astronauts proficient in ARIS radio ops and our ground stations proficient to support ISS backup communications. ARIS remains truly grateful for the support and contributions from our sponsors. This includes our space agency sponsors, NASA SCAN and the ISS National Lab, who ensure that we have launch and landing opportunities and crew time on ISS. Our amateur radio leadership team, including ARL and AMSAT, that provide financial and in-kind support to our program. And a special shout out to ARDC, who have provided critical resources to allow ARIS to excel in our education outreach to teachers, students, and the community through our contact operations, teacher and youth workshops, and the deployment of the Stereo Sparky radio kit to educators worldwide. Ham radio has been operating on human spaceflight vehicles for over 42 years. We've evolved and moved our systems as the space agencies have evolved their human spaceflight vehicles. Starting with the Space Shuttle in 1983 and moving into the Mir Space Station, now on ISS, and most recently through the FRAM-2 mission on the Crew Dragon capsule. ARIS is staffed almost exclusively by an international volunteer team. Our three-pillar initiatives, which are integral to our program, include STEM education, which drives the development of the nation's and the world's STEM workforce, spaceflight hardware development, and spaceflight operations. ARIS 2.0 represents our overarching vision for the future. We want to provide more extensive educational outcomes for all. That includes students and lifelong learners. In other words, you. We will accomplish this through engaging educational projects and lesson plans. We will expand our human spaceflight reach into commercial space stations and lunar orbiters and landers, while keeping a focus on our ISS program until ISS end of life. Some of our ARIS 2.0 initiatives underway include the fact that the ARIS payload is now a facility on the International Space Station. This enables partnerships employing parts or whole pieces of our ARIS facility. We have also expanded our initiatives to include Axiom commercial space station flights and ham use in the Crew Dragon via FRAM to ham. We are conducting more SSTV opportunities for hams and non-hams alike. and we have new educational initiatives in use or in production, such as Stereo Sparky, sponsored by ARDC, ARIS Star, sponsored by the ARL Foundation, and Student Mission Control, sponsored by ISS National Lab and the National Science Foundation. ARIS 2.0 represents a new hope by infusing a new generation of amateur radio operators into the hobby and into the STEM workforce, and exciting opportunities for hams the world over. 2025 has been a banner year for ARIS. Our accomplishments illustrate that ARIS has made significant progress on the realization of the ARIS 2.0 vision. Here's some of our accomplishments. As previously stated, we're celebrating 25 years of continuous operations on ISS. We've performed 59 school contacts to date and completed a record 6 SSTV events, including the Fram to Ham Polar Puzzle. And Ham TV is finally on orbit and operational. And we're keeping the ISS lights on for you day and night with 24/7 simultaneous ops of the voice repeater and APRS. Along with AMSAT and others, ARIS sent the FCC comments protesting the AST Space Mobile's use of 75 centimeters for satellite operations. Our SARX flight hardware was showcased in a temporary exhibit at the U.S. Space and Rocket Center Museum, located next to the Marshall Space Flight Center and Space Camp. 2 members of the ISS crew were on the air during field day, and Mike Fink and others have been heard on the voice repeater. This is your chance to make an astronaut contact. And I'm happy to report that ARIS sponsored Hope Lee and Ruth Willett to prepare and present a paper at the Space Ops International Conference in Montreal, Canada. They won Best Paper in the Youth Session. Congratulations, Hope and Ruth. And we have 3 major projects that were accomplished this year. These include the pioneering Fram2 mission, the first in a Dragon capsule. We supported the Axiom 4 commercial spaceflight to ISS with 3 international private astronauts on board. And we supported the Italian space agency Quascom and NASA on the successful NavCom experiment, a lunar GNSS experiment using ARIS LS band antennas. The Fram2 mission was a 3-day private astronaut flight in a SpaceX Dragon capsule. Fram2 was the first human spaceflight to fly over the North and South Poles. ARIS collaborated with the Fram2 crew on an activity called Fram to Ham. Fram to Ham employed all ARIS capabilities in close collaboration with the Fram2 astronauts and SpaceX to ensure Fram to Ham mission success. Fram2 was launched from the Kennedy Space Center on March 31st at 9:46 p.m. EDT on a southern trajectory into polar orbit. The mission landed in the Pacific Ocean near Oceanside on April 4th at 9:19 a.m. Pacific Daylight Time. Fram2 included a crew of 4. Rebecca Rogue was the ham on board and our Fram to Ham customer. Others, including Eric Phillips, supported the Fram to Ham activity. Rebecca was previously licensed in Norway, and ARIS VE team helped Rebecca get her license in the U.S. since the Dragon is a U.S. carrier, and it was not clear whether she would be conducting school contacts that needed a youth license. ARIS worked with Rebecca and her team on a youth experiential learning initiative that could be accomplished in her short 3-day mission. Fram to Ham was an SSTV competition for 16 to 25-year-old students. 12 Robot 36 images were transmitted during the flight with a twist. Each image represented a puzzle piece from 3 historically significant regions of the poles. The objective was to capture all 12 puzzle pieces for per polar region and solve the puzzle. All educational institutions were required to register to compete, we asked each team to be composed of 3 to 5 educational institutions and let them know that geographic diversity will increase their chances of winning, as there are only 1 to 2 good passes over each location per day. So international teams were encouraged. Discord was used for the event preparations and real-time communication during the short duration flight. There were 2 parts that needed to be completed to successfully submit a valid entry. So all teams needed to follow the competition manual carefully. During part 1, formation of international teams needed to be completed before the Frame 2 mission started. Then during the mission, each team needed to capture the 12 SSTV images and submit them to the SSTV gallery. In part 2, the teams needed to unscramble the puzzle pieces into 3 geographical locations, identify each polar region and the historical significance of that region, answer location-specific polar history questions defined by the Fram 2 crew, and submit the TESMA's team entry form. ARIS supported Rebea's mission and the Fram to Ham initiative in the following ways. In concert with the Fram 2 crew, we developed a comprehensive competition manual that could be used throughout contact preparation and operations. At the Fram to Ham informational webinar, we described satellite operations best practices and answered any lingering questions. We supported the moderation of the Discord channel and provided key information for Frame to Ham participants, including youth and others, on Discord and on the ARIS website. We instilled a test like you fly mindset in the youth, something that the space agencies do to ensure mission success. And we supported the team registrations, and when all the team inputs were submitted, we compiled the team results. ARIS Frame to Ham flight operations support included the development of pre-flight Keplerian elements. Thanks to a near-perfect trajectory, these pre-launch KEPs were good through the bulk of the mission. We modified the ARIS SSTV gallery to keep all Frame to Ham images cloaked until after the mission was over to ensure competition integrity. And we awarded a special certificate to all Frame to Ham participants that submitted SSTV images. During Frame 2, the ARIS Flight Ops team also supported another well-known ARIS capability, school contacts. Rebea conducted a successful voice contact with TU Berlin. With this, Frame 2 demonstrated 2-way voice contacts and SSTV downlinks. ARIS also provided real-time mission updates on Discord and through social media. One of the final mission updates is particularly noteworthy, stating that this amateur radio experiment, our first in a Dragon capsule, was incredible. It far exceeded our wildest dreams. Fram to Ham employed an ICOM IC705 and an existing Dragon antenna for 70 centimeter operations. The ARIS engineering team developed a matching circuit for the antenna and provided a flight and flight spare of that matching circuit for the mission. A key contribution to Fram to Ham was the use of new automation software and a Surface Pro computer that leveraged ARIS FlowScan television software developed by Chris Thompson. Chris also integrated some new features in the package to minimize crew workload and maximize the voice and SSTV capabilities of the system. This image represents the automation software that was developed for Frame 2. ARIS wants to give a special shout out to Chris Thompson, VE2 TCP, for his exceptional automated SSTV software used on Frame 2. Thanks to one of the Frame to Ham teams, here's the solved puzzle with outstanding downlink reception of all 12 puzzle images. The 3 polar locations are Antarctica, Franz Josef Land, and Svalbard. For a 3-day mission, the outcomes of Fram to Ham were historic and spectacular. We had 718 Discord participants, 14 international teams, and 55 educational institutions that registered for the contest. We estimate that each student spent about 25 to 50 hours learning about ham radio, satellite operations, and polar exploration. We had about 308 pictures submitted to the gallery by the competition teams. A total of 1,833 SSTV submissions were submitted by all the listeners worldwide. This is outstanding for a 3-day event. I mentioned the youth's learning. Take a look at the breadth and depth of the coursework assigned to the competition teams. We received a lot of feedback from the youth participants, and it was all good. Some great quotes included, "It's neat to be able to share a bit of space history and be part of the research. Events like these should be more often. Yes, there are many SSTV events, but competitions riddles that bring together the international community is a great enabler for radio education." It also got my friends genuinely excited about the communications technology and the space industry. The Axiom 4 flight represents our latest venture with private astronauts on a commercial spaceflight mission. The Axiom 4 Crew of 4 were launched on June 25th, 2025, with splashdown on July 15th. It should be noted that nominally, a maximum of 3 private astronauts participate in ARIS events. Each of the Axiom commanders, while ARIS alumni on ISS, want to focus on the mission success of each short duration mission. ARIS started working with Axiom on their private astronaut missions in 2021. We've supported 4 Axiom private astronaut missions, about 1 a year, with Axiom 1 the first flight, launching in April 2022. These are all short duration flights, which are significantly more challenging to schedule. We cannot predict the pass times until launch occurs, and the ISS crew schedule is not 24/7. As you can see, the first 3 missions included astronaut hams from Canada, Israel, Saudi Arabia, Sweden, Turkey, and Italy. For Axiom 4, we conducted 6 school contacts, 2 each for private astronauts in India, Poland, and Hungary. These ARIS experiences are huge events for each private astronaut's home countries. From an ARIS perspective, this mission was particularly demanding. The launch date and time put the ISS in a ground track that required all contacts to be performed by our K6 DUE station in Greenbelt, Maryland, all in the early hours of the morning and during the July 4th holiday. Our compliments to K6 DUE and all their team, as all the contacts were outstanding. As we work with the commercial space station companies, we let each know that one of the most important items that need to be added to their vehicle soonest are antenna feed-throughs and mounting fixtures. This chart describes how we are conveying this to the companies. We also let them know that we will supply the antennas and feed lines, and we will provide antenna system integration and flight certification support. In 2021, ARIS became a facility at ISS. That means that others can utilize our onboard resources through a written agreement with NASA that needs to be approved by ARIS. Our first on-orbit use of our facility was with Axiom. In 2022, NASA asked ARIS to work with the Italian Space Agency and Quascom, an Italian GNSS manufacturer, on the NavCom experiment. They needed our L-S-band antennas, cabling and equipment and expertise to perform their project. The NavCom experiment was launched to ISS in late 2024 with installation and deployment in spring of 2025. The objective of the experiment was to perform an in-situ demonstration of lunar navigation reception using Quascom's Positioning, Navigation, and Timing Receiver, or PNT. The Quascom receiver, with its embedded software-defined radio technology, and ARIS's S-band antenna system on the ISS processed navigation signals sent simultaneously from 5 ground stations on Earth. The experiment was a great success and paves the way for future experiments as well as future introduction of GNSS-like constellations around the moon to support navigation and timing in cislunar space. I'm pleased to announce that after a 7+ year hiatus, HAM TV is now back on ISS and operational. The efforts to recertify HAM TV were extensive, with repairs required in Italy, multiple tests conducted at NASA to ensure the unit met the more stringent EMI test requirements, and delays because of COVID. Part of that work included the development and certification of a HAM TV filter shown next to the HAM TV unit with Johnny Kim in the photo. This filter provides sufficient EMI requirements margin. If all goes well, we intend to start employing HAM TV with schools as early as this Saturday. We are looking for individuals and organizations that may be interested in supporting our HAM TV network of ground stations, particularly in the United States and Canada. Our best source of information for this is on the BATC wiki and on the ARIS Discord channel. NASA recently released a Request for Information, or RFI, soliciting organizations with ground station capabilities to inform NASA on how they may be able to execute tracking of the upcoming Artemis II mission planned for no earlier than April 2026. The intent is to perform one-way carrier signal Doppler tracking in the S-band 2200 to 2290 MHz frequency region. This is a passive activity with no transmissions required. There's no telemetry collection as part of this RFI. The RFI input should be less than 5 pages, and input is due October 27th at 5 p.m. EDT. For more information, click on the URL on this chart. If you recall, Amateur Radio Exploration, or ARIX, was formed several years ago as an international amateur radio project with team members from AMSAT and ARIS. Our goal was to jointly develop hardware, operations, and STEM education capability to support lunar operations. The ARIS team is suggesting the development of an ARIX consortium of ground stations to support NASA's Artemis II one-way Doppler RFI initiative. The ARIX consortium would demonstrate the robustness of a coordinated amateur radio international ground network that would be more robust than individual ground stations, and it would provide one amateur radio voice into NASA. ARIX big dishes like BOCM and others will ensure the Artemis II tracking requirement will be met. This approach allows some team members in the consortium to test and experiment with new ideas, including smaller dish antennas, in other words, smaller than 9 meters, and weak signal techniques that might augment 3 or 4 big ARIX dishes. Team members who want to be part of the ARIX Artemis II ground station consortium can submit individually to the RFI, which should state in their submittal that they wish to be part of the ARIX ground station consortium. Please contact Frank Bauer at frank.bauer@arisusa.org if you want to be part of the consortium. Our Discord channel is a great way to learn the latest ARIS news in real time, discuss probing questions, and meet new friends. We have sub-channels for APRS, SSTV, voice repeater, ham TV, and other general topics. We have over 830 people online since late, and we continue to grow. We encourage you to follow ARIS on all your favorite platforms. We're on Facebook, X, formerly called Twitter, Instagram, YouTube, Discord, Blue Sky, and LinkedIn. Given the pioneering work that the AMSAT AO40 team did to show the utility of GPS in high Earth orbit, I wanted to take a moment and recognize the Lugray GPS GNSS mission to the moon. Weak signal navigation in cislunar space and on the lunar surface is now a reality due to the research that was enabled by AMSAT's accommodation and operation of GPS on AO40. On behalf of the worldwide PNT team, I thank you. As I close this presentation today, let me say that together, AMSAT and SARC's ARIS have pioneered human spaceflight amateur radio, providing ham radio hardware systems for the shuttle, Mir, and ISS. And now we're certified on the Dragon capsule. Together we've been working diligently on beyond low Earth orbit ops, including lunar opportunities via ARIS. The recent NASA RFI is another way for ARIS and AMSAT to collaborate together on another ARIS activity. Together, we've developed outstanding human spaceflight STEAM education programs for youth and lifelong learners. Our thanks to Alan Johnston for his collaboration with ARIS over the years, and Mark Hammond before him. ARIS 2.0 provides youth and lifelong learners 24/7 inspiring, engaging, and educating activities for participants around the globe. And when ARIS and AMSAT collaborate, we do amazing things. For more information about ARIS, please visit our websites. As I close, I want to express our heartfelt thanks to those AMSAT individuals that have donated to ARIS over the years. I think you can see that your donations represent a strong amateur radio investment in our next generation. Thank you for your time.
All right, our next presenter coming up is Frank Karnauskas, our VP of Development and newest director to the AMSAT Board of Directors. He's going to be talking about Youth Initiative, and let's see what else we got coming up. We've got one, what? Jim White's, he's actually here. Oh, yeah. And then after him is ARDC presentation by Jim White. But this evening, we are having a social get-together and auction at the patio, which I wasn't sure where the patio is, but I understand it is right outside the main entrance to the hotel. Just as you come out that door into the courtyard area, there's a courtyard right there. That's where we're going to meet, and that starts at 7 p.m.
If you walked in the pool, you went too far.
Well, it depends on your intent. We could have a pool party. Yeah. All right, you ready?
I am.
Okay, I'm going to turn off my microphone and let Frank do the rest of the talking.
Well, good afternoon, everyone. Thanks for coming out to Phoenix. I hope you're enjoying yourself. We timed the weather just to be absolutely perfect. So this mid to high 80s is just great. By the way, if you haven't noticed already, during the day it's nice and sunny and it's nice and warm, and as soon as the sun falls below the skyline, it gets pretty chilly here. So you might want to bring a coat with you. I hope they have the fire pits going out there, and that'll help keep us warm out there. But it's just, I really love this facility. It's really working out well. Well, anyway, as Robert said, I'm responsible for the AMSAT Youth Initiative. And why do we have a youth initiative? Well, look around the room and see how many young people we have in the room here. Not that many. So the reason we have the youth initiative is the right thing to do. Okay, we need to replenish the ranks as time goes on here. And I want to point out just a couple key things about the youth initiative. I think the most important thing is it's a community-based program. Why is that? Well, the gold standard, of course, is when we can get amateur radio involved in the school systems. But if anybody has ever tried to work their way, an amateur radio program into a school. Not all the schools are excited about doing that, okay? Sometimes some of the school boards are pretty rigid in terms of managing the curriculum and that. We have some great teachers out there. We have some great examples, but there's just not enough of them, okay? So we don't want to let the schools stand in our way of success. So as a community-based program, these are standalone materials that any parent can use, any scoutmaster, future farmer association, all that kind of stuff. This is available for everybody, and it's designed to be used by everybody out in the public, okay? These are all open access materials that we offer for free, okay? A lot of the materials are, I should say most of the materials are harvested from federal government sources or different colleges who make the materials available for use on a non-commercial basis, and that would certainly be us, okay? So we take these materials in whatever raw form they're available, and we format them in a certain way, and you're going to see what we do with them. We are going to promote the heck out of these, okay? We're not talking about a dozen kids here or a dozen kids there. We're looking for participation with a lot of significant digits, okay, in who's using this. And what we have, where's David? There's David in the back of the room there. David Vine, our Director of Public Relations. The reason God invented him is for David to push these educational materials out to the homeschooling organizations and even the schools, okay? You know, if I said, you know, it's a community-based program, but if a teacher wants to use them, God bless them, the materials are there for them to use, okay? Something else that we're very excited about is these materials are designed for global distribution. These are not designed just for use within the United States. We use a software system that converts the content into the online materials. Back in about April or February, something like that, a gentleman, a retired high school science teacher, Eric Sonnenfeld in New Jersey, made the mistake of emailing in and said, I'm not an engineer, but I'd like to volunteer and do something for AMSAT. I said, Eric, have I got a deal for you, okay? So what Eric does is he harvests the materials, he formats them roughly, okay, into the format that we need, and then using this the software system that we purchased, I'm the one so far who has been converting these to the online materials. Now we have a grant request into the RDC for a couple more licenses, so I'm not the bottleneck anymore. We can get a couple more people involved, and also to upgrade our license. We have kind of a basic license which allows us to do some amazing things, but with an upgraded license that uses some AI facilities, it will take all of the content that we developed in print and add audio to it. It'll actually read the material, and I'll show you an example of how that works, okay? And last thing I want to mention about the youth initiative is it's the foundation for our development efforts in the future, okay? Because if I go out there as the VP of development, which is the politically correct term for money raker, okay? And I say, okay, I want some money to build a satellite so Mark Hammond there can work on his Gridmaster Award. The line of people wanting to donate money for that is pretty short, okay? But if you have a mission that is worthwhile, that benefits the community, educational mission is the low-hanging fruit, okay? And there's plenty of money out there if you show the potential grant maker that you've got a worthwhile program that's going to benefit a large body of people. Okay, so we've got our youth initiative is really delineated along two different lines for the younger kids. No, I'm sorry, for the teenagers. We call it BuzzSat, and this is a registered trademark. that we have, and we also own the domain names for BuzzSat. And if you ever tried to find a domain name, okay, that has sat in it or satellite, good luck, because the domain name squatters have gotten just about everything wrapped up. But we were lucky to find BuzzSat as a name that we could register the trademark, and the trade name was available. So, and I have to thank Robert. Robert, where are you hanging? There he is, back in the corner. My original proposal for the name was Cubesat. Okay, another cool name, which we could register the trademark and had the domain name. But Robert very astutely said, you know what? Teenagers don't like to be called kids. Okay, so it was back to Google and back to all the other domain name search facilities, and that's where we came up with BuzzSat. So Robert, thank you for catching that error early on in the game. Okay, so in BuzzSat, there actually is a live BuzzSat website right now, buzzsat.com. And if you go look at it, you're going to say, oh, you know, this content is really kind of hokey. And I will be the first one to admit it is, okay? But what we needed to do was get a website live with the BuzzSat name, so when the trademark inspector went around to see if this was actually a legitimate name that was being used in commerce, that's why we got the BuzzSat name out there. Now, what we have added, though, I'm very proud to say that Hamvention, if anybody was there, we launched the first iteration of our first online course in satellite technology. We've got about 14 different courses that are in production, and I'll show you a little bit about that. But the first one is satellite introduction to satellite meteorology. Well, what does this have to do with amateur radio? Well, if you walk into a room full of kids and say, hey, anybody here interested in amateur radio? They don't know what amateur radio is. You know, they didn't know their smartphones are radios. So instead, what we have to do is throw the net out there to try to cast a wider group of people and in areas where they already have an interest. Okay, so we're going after hooking them in the interest that they already have, and then we kind of sneak the amateur radio in there as we go along the way. Okay. Now I'm going to show you. I don't dare do a live demo. Okay, you know how that works, right? So I'm just going to show you a couple screens here. These are serious courses. Okay, there's about, and this one's even the next to last iteration. There's over 300 pages in each of these courses, so there's a serious amount of effort that it takes to go through each of these. Now, this is what's, I think, really unique about our courses. Most online courses are just electronic page turning things, okay? And what we did not want to have happen are the kids half asleep doing next, 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 next. So on each, having to read a long paragraph, fall asleep. Okay, we just have 2 or 3 sentences on each frame. Okay, and then they have to answer a question. And they're not tough questions. Some of them are even silly questions. We don't care. We just want to make sure that they're paying attention before they go ahead. So some of the questions are true and false questions. They answer correctly and they can move on to the next frame. Some of the questions are multiple choice. Okay, and if they answer incorrectly, they get another try. They can take 12 tries if they want to answer a four question, multiple choice question. We're not tracking these questions that we can later on, okay, but we just didn't want to try to take 4 years to make it perfect. We just wanted to get something going right away. And I think we ended up with a pretty good product anyway. Okay, so after they have 8 or 9 tries and they finally get the question correctly, they move on to the next one. The other type of question is they have to identify something in a picture. Okay, so it's just simply click on the solar panels on the now obsolete and decommissioned. We have a little updating to do since this slide was made. Okay, show us what a solar panel looks like. Okay, so that's kind of the way it works. Any questions so far? Okay, I got a lot of time for questions. This is not death by PowerPoint, okay? Okay, so here's a list of the courses that we're developing. We actually have the first 4 completed. Introduction to Satellite Meteorology, Satellites and Climate Change, Pollution Control, Satellites Protecting Wildlife and Natural Resources, and we have content subject matter experts for about a third more, and we're looking for more, okay? So if anybody out there at home is a competent expert in any one of these areas, we'd sure appreciate your help. So our intention is we will have the first 4 courses on by the end of this year, and then by the end of 2026, we'll have 14 courses done. Okay. Now, if anybody thinks, hey, you know what, you should have a course on this, that, or the other, we'd love to hear from you. Okay, we can grow this list forever and ever. And you notice down here, whoops, wrong button. Okay, okay, and they don't have to take these courses in any particular order. Okay, so if we catch their interest and they're interested in satellite telemetry and management, well, we're putting together a course on Fox Telem. Okay, and amateur satellites. So, and actually what that means is a ground station. Okay, how to put together a ground station. One of the things that I don't have on the slide here because it's not ready yet, but we are actually supersizing one of Alan's Cubesat simulators that he'll be talking about tomorrow, and we're going to stream this data live, okay, because there's only, 200 Cubesat sims out there, Alan? Okay, but we want 10,000 kids to experience using it, okay? So we're going to stream the output from a Cubesat simulator, which is orbiting my laundry room at home, okay? So we've had to arrange the lighting and everything so it looks like it's actually in orbit. But, they'll be able to download the telemetry with Fox Telem, and the courseware teaches them what the telemetry means and how they can use what they can do to analyze it. Okay? So, I threw this picture in there. I'm so proud of this picture. Like I said, we introduced the Introduction to Satellite Meteorology at Hamvention this past year, and this was about noon on Sunday. Hamvention was just closing up. Everybody's going home. We want to pack up. We want to go home. We've been standing around and yammering for a couple days here. And this family walks into the AMSAT booth there, and the father, who is the obvious ham in the family, walks over and talks to some other AMSAT people. And this little girl just no encouragement from her parents or anything, just walks over and sits down at the computer, okay, and starts working the problem. And the mother came over. She was on like 20 minutes, and you can see the look on her face. She's not a little kid just looking for, some visual stimulation. She's working the problems, and we worked so hard to get this ready for Hamvention, but when I saw that happen, it just made all the work worthwhile. And I just kind of I sent this to Erica, our developer back in New Jersey. It got our batteries, recharged, and said, yeah, I think we're onto something good. So that was warmed the cockles of my heart, as they say. Any questions on the BuzzSat program? Okay, now we come back to the kids SAT program, and this is for preteens. And to be honest with you, originally my vision of the youth initiative was for teenagers. And talking with Frank Bauer, he says, no, you gotta get them by the time they're in 5th grade, or you've lost them. Okay. So came up with, said, okay, I'm glad we got the KidSat name. We're gonna do something with it. But my head was just scratching. I couldn't figure out what to do. But then, what could be more fun than a coloring book? Okay, so if you noticed, if you kind of remember what the list of topics were for the BuzzSat program, well, the KidSat program mimics it, follows it pretty closely. You know, a little bit different tone on some of the subject matter, but you know, the whole thing, theory of the program is satellites in space help us live a better life on Earth. Okay, so the message that we're telling the kids is, okay, no matter what career you're interested in, whether it's you're interested in a career in the military or any branch of science or communications, think of something in our modern life where satellites don't play some role, right? Okay, so the message to the kids is, if you plan to exceed in any one of these areas, you should know a little bit about the role that satellites play in our lives. So, again, here's a list. Now, what this is, you're going to see, is there's 14 spreads. There's 14 two-page spreads. And I'm going to just jump to one right now. Okay, so we've got the cover completed, and we're working with an artist, Brad Peterson, who's in Tucson, a very accomplished animator for in a movie production in Hollywood, and that super great artist. You can see the he's really a great cartoonist. I'm really happy with the way this came out. Okay, so what we're doing now is developing the sketches for each of these 14 pages. So the message, each of these is kind of an if-then proposition. So for the satellite meteorology, it's satellites in space help us predict the weather so we can play safely outside. Okay, another one is satellites in space help the farmers grow food so we have plenty of healthy food on the dinner table. People get, one of the topics was search and rescue, right? Okay, so there's a little story about what happens when planes crash or people get lost, how search and rescue functions on satellites help find the people and coordinate the rescue. So it's just little homilies like that that kids can understand. Okay, we're not concerned about was it P104 connectors or whatever you guys were talking about. You guys have to understand, my dream in high school was I was going to become an electrical engineer. I was going to marry Mary Lou, who lived 2 doors down, okay, and have a cabin cruiser. I lived in Chicago on Lake Michigan. And my first calculus course ended my engineering career. It just cut me off at the knees right there. So I had to find something to do, so I ended up in advertising and marketing. So does this make sense? Just kind of appealing to the kids in a broader sense. And even in the coloring book here, we'll jump back here to the list of different topics, and we think it'll be fun. We have a grant request into ARDC for this, but I couldn't stand to wait, okay, for them to make up their mind. We just said we're going to publish this thing for one way or the other. But in a conversation with some of the people at Hamvention, they said, "Oh God, this is great. We want to make Hamvention more of a family-oriented affair to give some reason for kids to come." So this person said, we might just print up a couple hundred or 1,000 of these and just hand these out to the kids when they show up at Hamvention. I think the other thing that we want to do with these is find corporate sponsors from the radio manufacturers or other companies in aerospace to fund the printing of these things and distribute them wherever we can. But the coloring book itself initially will be available online. Okay, so mom and dad can download the whole 28 pages of coloring, or they can just download one spread at a time. And at the back of the book, okay, there's an information page. okay, on each of those 14 different topics in the book. So if they want to sit down with their child, and it'll have a list of resources in there, so if they want to kind of continue the conversation or the dialogue with their kid and suggest some other activities they can do in any one of these areas, this little leader guide, I'll call it, there's one of those for each of the spreads in the book. Okay, so that's kind of what that looks like. Oh, you know, I want to jump back here. We believe in DEI. Okay, when I said this, you know, we're showing kids of different cultural heritages. There's a couple reasons for this, but we believe in it, and this is going to be globally available. So working with the other AMSAT organizations throughout the world will make this available to them. Because these upgraded licenses that we're requesting from ARDC includes a facility in them to convert these into 71 different languages. Okay, so we can produce these coloring books in virtually every language on the face of the earth. Okay, so that's why we wanted kids to look like kids all over the world. Okay, so and again, you know, aside from this being the right thing to do, because we need more kids in STEM topics and in amateur radio, this is how we raise our money. Okay, like I said, it's not for Mark to get his Gridmaster Award, it's to help encourage kids to take careers in science, technology, education, math, and art, okay? So that's it. Any questions? Comments? Guess who's next, Mr. White? So how was that for an intro for your presentation?
Wow. What he does amazes me. I also should have listened to him before I put this presentation together, because that's the only picture in the presentation. The rest of it is death by PowerPoint. Unfortunately, granting money is kind of dry in many cases. I did want to point out, since I tend to like to start with that picture, Frank Bauer was talking about being able to use GPS from Earth for the navigation to land that lander on the moon. On AO40, those are the GPS antennas, 4 of them, that Frank's group at NASA Goddard provided to AMSAT to fly on the satellite, where from 60,000 kilometers, we were able to look back at the Earth and receive GPS signals. And not only that, we were able to map the side lobes of those helix antennas on the GPS satellites and prove, but all that data went to Frank and his group, of course, and prove that you could, for the first time, navigate using GPS from above the constellation, because you're seeing the satellites around the other side of the Earth. And where is that now? Everybody in orbit navigates with GPS, right? Okay, so ARDC. I'm fairly new to ARDC. I joined the Grants Advisory Committee just about a year ago, but I just want to talk with you for 20 minutes or so about what the ARDC Foundation is, what it does, give you just a brief history, which is really kind of fascinating, describe our mission, vision, the strategies, But then I want to focus in on priority areas for funding that were developed earlier this year, and especially those related to space. And we'll talk a little bit about how to apply, how you get your application in. So the ARDC Foundation, it's a private foundation, it is a 501c3, and it was created for the purpose of promoting amateur radio and promoting digital communications. So the areas that we focus on are learning, experimenting, and doing, and I'll define those a little more in a second. But keep those in mind, learning, experimenting, and doing. In addition to that, we manage 44net. So any address, any IP address starting with 44, except for the ones that we no longer own, are dedicated for use in amateur radio. So there's about 12 million of those addresses that are available. If you're doing an amateur radio project, you need IP addresses. These are available for you to apply for, and there's a whole process for doing that that's defined on the website. Excuse me, the bottom line is, because we have a fairly substantial endowment, we are able to grant out between $3 and $5 million a year on average for amateur radio or digital communications projects. So let me explain this intersection between amateur radio and digital communications. If you look at our logo down at the bottom, you'll see there's a bar in between the AR and the DC. This is B. Dale Garby, came up with this. That is a logical inclusive OR symbol, okay? And I love B. Dale for it. B. Dale's my good friend, but it's confusing to many people, so let me explain it. We work in the area of amateur radio. We also work in the area of digital communications. We work each of those individually, but also at the intersection between those two. So the point here is that a project, an application that you apply for funding for, does not need to be digital. It can be pure amateur radio, okay? Or it can be pure digital that doesn't involve amateur radio, as long as it meets the other criteria that we're concerned about, you know, open source, et cetera. Or it can be both. So amateur radio or digital communications, either or both. So a brief history, a kind of an amazing story really. In 1981, there was a thing called ARPANET, and Hank Manguski was one of the guys who was dabbling in this business of what do we do with this address space in this thing that we have invented called the IPv4 addressings, right? IPv4 is what we're all familiar with, 192.168.1.1, that's an IPv4 address, right? In 1981, ARPANET was slicing up those addresses and allocating them to different uses. And we were beginning to experiment, we hams, Phil Karn and others, with packet radio. And the guys who are really into this are looking at what's happening in the internet world, and they're saying, you know, we could do that also, we kind of already are. So Hank Manguski called up the guy who was allocating the IP addresses, and he said, hey, you know, hams are kind of working in this area, can we have some addresses? And he got 44.anything assigned to amateur radio forever, right? In that day, there were 12 billion addresses, as I recall, and in those days, nobody believed that the world would ever use all of those, so this was an okay thing, right? In the process of doing that, then they had to put together an organization to manage those addresses. So Hank and some others put together AMPERNet as the loose organization of volunteers to manage the addresses, to give them out to people. In 2011, things got a little more complex, and ARDC, or as an organization, was formed to be the trustee of the 44 net addresses. Brian Cantor, of course, was a big part of that. In 2019, Brian and the other folks involved recognized there was a real sweet spot here because IPv6 was coming, which has, I don't even know what the right term is, 100 big Catian addresses, right? More than the world will ever use. We've heard that before. And IPv4 addresses, however, IPv6 was not fully adopted yet. It was not available in many places. So IPv4 addresses were worth a lot of money because at the same time all that was happening, there were some of these companies building all sorts of cloud and web services, and they really needed IPv4 addresses. So these guys said, there's an opportunity here, and they sold off a third of the addresses and created the endowment that now funds ARDC Foundation and funds projects. There was, right after that happened, Brian unfortunately passed away, so the other folks that were involved in that, B. Dale and Phil and some other folks, had to put together fairly quickly a set of processes to give away 5% on average of that endowment every year. That's the IRS rules for charitable foundations. So they did that. They had recognized pretty quickly they needed to put together a little bit of a staff. I think we have 8 paid on the staff now. It's a very slim organization. The majority of the people that do the work are volunteers. But when you're dealing with these sorts of sums of money and you have to stay straight with the IRS and everything, you do need a little bit of a paid staff. So that happened on through 2020, and that is the organization today. So some statistics from 2019 to 24, we gave out 315 grants totaling about 30 million and impacted by, I think, a fairly conservative view, over 94,000 people directly impacted by those grants. If you look at the annual reports and all of this stuff, the audits, everything is on the website. In 2024, there were 198 proposals submitted, 59 were funded, and about 3 million, a little over 3 million was distributed. So this is really dry, but this is the basis on which ARDC operates. The mission, I'm not going to read it, but it's all about enhancing, promoting amateur radio and or digital communications in all of those areas. It's about open access, innovation, education, and enhancing communication technologies. Our 3 strategies, and we kind of tend to bucket grant applications that come to us into one of these 3 buckets, although there's often quite a bit of crossover: promoting learning, experimenting, and doing. So what's learning? It's getting more people educated, learning about AR and DC. So obviously that's STEM education, all the way, all the kinds of things Frank was just talking about, all the way up through universities, university Cubesat projects, university curriculum, etc. Experimenting is all about R&D. We have funded some fairly substantial R&D projects, for example, having to do with digital voice. Amazing what those folks are doing with digital voice. If you haven't seen those demos, you should. So we've seen all sorts of very interesting R&D projects. And then promoting doing. Doing is operating. And the objective is to get more people involved in using more different bands and modes and technologies. So the kinds of things that fall under that category our emergency communications trailers, rebuilding club stations, rebuilding repeaters and rehabbing and new repeaters and networks and those sorts of things. So there are some other parameters that we have to deal with, of course, and that is that we will not fund anything that is a gatekeeper technology where you have to be licensed or a member of a group or something to participate in that technology. We are looking for the broadest possible impact, not something serving just a single group of people. We like things that aren't likely to be funded by other sources, and especially in the digital communications part, it does not necessarily have to be wireless. If somebody came along with a really interesting, advanced, the state-of-the-art wireline digital R&D project, for example, we would take a look at that. So earlier this year, the board of directors got together and formulated some priority areas of funding, and the idea here was to make it a little bit clearer the kinds of things that, as B. Dale says, are interesting to us. So in the R&D area, we are looking at, of course, open source solutions. You can see the list there. Imagine, we all know what the RTL dongle does for receive, right? Imagine something like that for transmit, the same sort of thing. There are a few out there. I run one on a ground station that I lease out to universities at LSB 200, but it's expensive, very expensive. Open source education means curriculum and the kinds of things Frank was talking about, developing curriculum and then putting that out in the public so that it's available for anybody to adopt. And that can take all those forms that you see there. And then in the area of space-based communications, I want to talk a little bit more about. Let me just jump ahead to the next slide. So an area of interest here, a priority area of interest, is higher orbits. And that can be highly elliptical or geo. I really think it would be cool to go to the moon, but I understand the difficulties involved in that. So geosyncs, hosted payloads on a geosync bird, standalone geosync, anything that gets us more coverage and more bandwidth would be an area of interest for ARDC. A little more specific, that could be repurposing commercial birds, it could be hosted payloads, and then of course, educational initiatives that use space. Some of the ARIS things that Frank was talking about, it just amazes me what ARIS has done over the years. That falls right into our area of interest. So just a quick look, a couple of slides of space projects that we have funded. You'll see these are pretty international. There is the Pathways to Space there, which is teaching teachers about space so they can teach it. Some Cubesats built by students around the world. Here's some more. Here's, of course, the one for AMSAT NA. The Birds X Cubesat and Kyushu. So you can see it's a variety of things, both educational and space-based. Now, these were all granted before the board readjusted those areas of interest, so we're looking for higher orbits now. If somebody came along with a grant request for a package to fly in LEO, say in a CubeSat, in order to qualify it for a higher orbit, in my view, I'm just one vote on the grant advisory committee, but in my view, that's something that we would take a look at. So, only two more slides here, I think. How do you apply for a grant? First of all, to be eligible, you got to be a nonprofit. These are the IRS rules, right? We're a nonprofit. We can only give to other nonprofits or government agencies, schools, universities. It includes clubs that are 501c3s. Certainly it can include individuals if they partner with that club, international groups. International folks that we have looked at have different rules, sort of, to define what a nonprofit is, but you still have to be a nonprofit. And we are not willing and interested in granting money to businesses or for-profit organizations. So if you're interested in applying, by all means go to grants.ardc.net, you click apply, it'll take you through the list of things that you need and the information that you need to provide. The way we work is we receive grants quarterly. At the end of the quarter, then the Grants Advisory Committee, there's about a dozen of us, we look at all these. It takes about another quarter to look at them and make a determination as to whether we will recommend them to the board or not. And at the end of the quarter, we send that list over to the RDC board and they make the final decisions. So here's some contacts. Back to 44net. Adam's address there is if you're interested in a 44net address. These are all at ardc.net. All that information is. But here's where you would find that sort of thing. So in summary then, the QR code there, I highly recommend. Our media people did what I think is an absolutely fantastic video. It's not very long. It is how ARDC and how 44net came to be, the history of it, in the faces and the voices of the people that were involved. I think it's a fantastic video. So in summary then, we're all about promoting amateur radio in the areas of learning, experimenting, and doing. And I'd be glad to answer any questions that you have.
All right, Jim, thank you very much. Since I had the microphone, let me be the first question. Number one, I want to thank ARDC. You guys do great work, funded some great projects. I enjoy watching the project award announcements. Some great stuff going on there. But I've seen different, or I've heard different things. Open access versus open source, and does it matter? I believe originally on the initial publication, it required it to be at least open access, which has a different definition than open source.
I think that's a difference without a distinction.
Okay.
Whatever it is has got to be open, so anybody
Gotcha.
can use it, anybody can take it and implement it. Doesn't necessarily mean that the code has to be open source, although B. Dale would probably argue with me about that since he is the god of open source, right? Yeah, I don't know that there's that much difference, Robert. The whole idea is we are not interested in funding things that then become a closed system that people can't use.
Okay, thank you. Next question, anybody? Oh, come on. All right. Thank you so much.
All right, thank you all.
Yeah, appreciate you coming down. Looks like that's it for today as far as the symposium's going. So let's talk about what comes next. Dinner is on your own, and then we're going to meet at 7 o'clock for the social get-together and auction. There will be, I call it light hors d'oeuvres. They'll be hot, stuff in the little pans that you can pick out and put on a plate, that sort of stuff. Not enough to feed you, but enough to kind of like keep you from consuming too much alcohol on an empty belly. There will be an open bar. Well, I'd say open bar. It's cash bar.
Big difference.
Yeah. But if you have a hotel room, they would prefer that you put it on, your hotel room, the charge for the beverage. That way, what? 301. Anyway, it makes the transactions go faster. If you have to use your credit card or pay cash, who knows if they have checks? Yeah, no cash, okay, so that makes it easy. So credit card there, then you have to use a credit card machine. But the auction that's gonna go on, I think there's a few items. And we will take cash, credit card, or online payment donations. So bring your money. That's the important part.
Bring your items if you have it.
Yeah, if you brought something to auction off, we'd appreciate it. If not, we will then meet again tomorrow morning at, oh my God, we're starting this thing at 8 o'clock, at 7:55. Who made this schedule? Frank? Okay, so then we will meet again here at 7:55 for the welcome, but I'll tell you what, 7:59 will be quick enough for me to say good morning, let's go next. And then we're going to start off at 8 o'clock with Alan Johnson leading his Cubesat sim update. Okay, any questions for tonight?
My wife says any of the spouses would like to go travel and meet her in the lobby.
Tonight?
At 8 o'clock or 9 o'clock.
Oh, okay, for tomorrow morning. So if you have your spouse, she's sitting there and she's tired of looking at the walls or hanging out at the pool.
Looking satellites.
Yeah, then, yes. All right. Any questions? Y'all been great. Thank you so much for coming, and we will see you tonight and tomorrow morning. Thank you.